there's some changes when it's exposed to that.
So now it's live.
Not a beat. It takes a long time. Ionization sort of stuff.
Dr. Reed, did you bring your camera? Okay, so this is broadcasting. Oh, there's another one.
It's kind of snuck in. You know where he is. Every now and then he pops up. He's here. Yep. Right.
Did you tell me that? No, that was United. That was United. That's
All made it.
Yep.
Are you amazed to see that people actually function?
Yeah, man. No, I was amazed. Where's Daniel? Did you take care of him?
No, not today.
Wow.
We're waiting for Dr. Cordero, right? And Dr. Palmer. You guys want to switch songs?
How about Eye of the Tiger?
Eye of the Tiger. All right, let's just wait a second for Dr. Cordero and Dr. Palmer.
So you did have, there was one conference paper a few years ago where kind of late at night, and I walked in. That song was on loop because he had like 8 hours to get his device working and write a paper to submit.
Man, that was last week. That was last
He did get it out and it got published, but I don't think I've listened to that song since.
It was the first couple of papers that were on last minute.
Now he's submitting them a month and a half early.
True, because
The deadline changed.
somebody's tricking me with the deadline. Which is a good thing. Not really tricking.
Just failure to pass along delayed information.
Alright.
There he
There you
is.
go, Dr. Cordero.
Oh boy, I'm ready.
So while we're waiting for Dr. Palmer, there's so much stuff back there.
You need to give your condolences to Dr. Cordero about Spain losing soccer yesterday.
Hey, oh, what happened?
I don't know what he's talking about.
What's that?
What happened to Bosnia?
Bosnia made it. That's good. We're good. Just doing it.
Oh, they are out of it.
Yeah. Oh man, Spain.
It's beautiful.
Yeah. You're so arrogant. You know, it was good. Like Terry's like.
Who's arrogant, Dr. Cordero?
No.
He's in denial. Don't bring it up next year.
And like I said, if you just grab you a donut or something, there's some nice, nice little cakes that my girlfriend made back there. Try those, right?
No, I haven't tried those.
Please try those. I have it. Your friends didn't even take it.
I did.
Okay, so we're waiting for Dr. Palmer. So after this, if anybody wants to go to lunch with us, I think we're going to go to Carabas. If you guys want to join, they might even have some World Cup games. Okay? So afterwards, whoever has time.
At the lab?
No, it's Carabas. You can come too if you like. I know I haven't been talking to you guys for like a month.
We just sit right there.
We just say good morning, and that's
That's
enough.
it. He hasn't gone to sleep yet.
Isn't it sleeping?
How many times has that happened?
Last week, all days.
I'm just hearing like sneaking around me.
Yeah, we're like, where's Ismet?
She's going to bed and everything.
We talked about using the Karen system for sleep studies, gently rocking people.
Waking up.
I said no, but we're going to talk to the sleep people. What are they upstairs?
Yeah. That's not a bad idea. It was kind of a little bit noisy. Just a little.
My question before we start, what's that REED lab? REED, what is that?
It stands for Rehabilitation, Engineering, Electromechanical Design. Lab.
Really?
Yeah, it's
Oh my
active.
God. I thought it was something else.
No, it's really coincidence that
It is, oh,
this
yeah.
lab existed for the last 30 years. Very coincidence, Dr. Reed.
You spend out of vacation, right?
Oh man, Dr. Palmer.
I'm texting. He didn't update his calendar. He still thought it was 2 p.m. From way back in the beer engine.
And my computer was set up at Pacific time, so I thought it was at 6:30 a.m.
That would be an impressive feat for most of my labs. Unless they wrap it up.
Yeah.
We should sit down. Video again. Challenge trainers over PhD. Maybe we should just.
It's really sleep study, right?
He's coming.
Cutting some of this wood pieces that he has.
Just rearranging them.
Rearranging.
That's the new hobby these days.
You're supposed to be sitting over here.
Good job.
So let's go around the room and introduce her. What's her major?
Why don't you just talk about yourself a little bit more?
All right, sure, that's a good idea. So my name is Ismet Handzic. I'll be presenting this dissertation, and a lot of it has to do with gait rehabilitation. That's actually the interest. I have to wait for Dr. Palmer.
We're not doing the technical
What if
side.
we,
How do you like?
how about we introduce the committee? There's a couple of them that I know don't know each other.
Okay,
So I'm pretty sure everyone knows
Dr. DeBay,
Dr. DeBay.
Mechanical Engineering Department.
Department chair of the MD department. I'll let you can do it.
Dr. Lusk over here. Dr. Lusk from Mechanical Engineering. And Dr. Palmer over here. Okay.
You finish going around. So Dr. Soon, Dr. Palmer, Dr. Portiero, Dr. Kim.
Yeah.
So these are the two that I know probably don't know each other as well. So I think everyone else around knows.
All right. So
since I'm serving the chair, and you already did a lot of the work, so make my job easier. And he also introduced himself. I just want to say, now we can start, and we get 45 to 50 minutes to do this, and then after that we have the questions from the audience first, and then we want to go to the committee, and hopefully after that we can wrap up. All right?
Thank you.
Yep.
Okay, we'll start. So today I'll be presenting the last 4 to 5 years of what I've been doing in Dr. Okay, so this is kind of a compilation of the whole thing. Okay. So to start off, like we just did, Dr. Rito here from Mechanical Engineering is my advisor, my major professor and my mentor. Dr. Lusk over here, he's from Mechanical Engineering. Dr. Portiero back there, Mechanical Engineering. Dr. DeBay over here, Mechanical Engineering. Dr. Palmer just came in, Computer Science and Engineering. And Dr. Kim over here for the School of Physical Therapy and Rehabilitation. And Dr. Soon, that was just speaking, is for Computer Science and Engineering. So, like I said before, so this is 4 years of work. And before I even get into this, I have to say, I won't be able to talk about everything. The details, how I did things, I mean, there's so many details, so many little side projects and things. In 15 minutes, it's impossible. So the dissertation I turned in, from cover to cover, including appendices and figures, was 330 pages, okay? So there's no way I can put that all in there. However, I'll try my best to be as clear as possible what I did and what it means, okay? So this is generally what I did. 3 big sections, big chunks of what I did. Three different things I can divide this up. One is the gait-enhancing mobile shoe for gait rehabilitation. Then kinetic shapes that stemmed from that idea was inspired by the gait-enhancing mobile shoe. And then also passive dynamics, which includes kinetic synchronization and also passive dynamic walkers. And I'll explain here in a bit what that is. So before we get into anything, I'd like you guys to understand a little bit about walking and also about the rehabilitation, asymmetric gait as rehabilitation. Okay? So let's dig in there. So the first step, right? So this is one step. Now I'm kidding. This presentation is not going to go this slow, right? But I want to make the distinction that this is one step and this is one stride, right? Okay? And just like this dissertation, this work is one step at a time, right? It's a stride and a mile, okay? So everybody's familiar with the human gait cycle, okay? You start by touching down the heel, you go into the stance phase, and then you toe off, okay? And right before toe off, you might walk your knee, and then you toe off, okay? The same thing happens 180 degrees out of sync on the other side, on the left, the right and left. In human normal walking, that's what it is. If you look at the spatial diagram, I mean the temporal diagram of how long something takes, this is what it looks like. So you have some double support phases where both feet are on the ground at the same time. So you have left double support, right double support. You have sometimes when one limb is swinging and one limb is in stance phase. Okay? When you look at the forces that you exert on the ground while walking, so if I'm touching down my heel, the ground exerts a force on my heel and I'm exerting a force on the ground. So this is what it looks like. So the force that comes up is blue right there. So it goes up to about body weight, fluctuates, and it goes down when you toe off. And then the force that keeps you from sliding, right, keeps you from sliding out, is the red right there. So it keeps you, it's a maximum force coming in when you start the heel, when you start heel contact. Then it's somewhere in between. There's no horizontal force. Gets to maximum right before toe off and you toe off. One concept that I like to stress are foot rollover shapes. Okay, and this concept is really important for not just gait rehabilitation, gait walking and things, also for robotics. Okay, for human biped robotics for walking. Okay, so a lot of times literature and approximations say that the rollover shape, which is the shape that you roll over with your foot, okay, the shape that you form when you roll over your foot, is 1/3 leg length radius. That is a standard, okay? So that is considered the most efficient and standard with a constant radius. However, a lot of studies, okay, have shown that that rollover shape is not constant. So that approximation does not hold. In fact, that rollover shape is dependent on a lot of things, like how fast you walk, are you about to start walking, are you about to stop walking, are you accelerating, even your age, okay? So all these things, your strength and stuff, can vary this rollover shape. So this constant radius is a little bit, maybe too much of an approximation, okay? So that right there was just a brief introduction to human normal walking, okay? When you get some pathological walking specifically, so there's a lot of pathological walking, all kinds of diseases and stuff like that, but I will specifically talk about gait asymmetry. And what that is, it's when one leg does not do what the other leg does. All right. So for example, if you have longer step lengths on the right than the left, then you might have, then that's a gait asymmetry. Anything from forces to spatial to temporal and things like that. Right? But the causes for that, it could be just it could just be natural. All right. So everybody has some gait asymmetry essentially within them. Right. So that could be the sport, because of the sport you play, the dominant foot you have, anything to whatever you do everyday life. So that could cause just a normal gait asymmetry. That can also be caused by leg length discrepancy, but any kind of spatial parameters that are changed. Dr. Reed likes to take the example of, if you right now take your shoe off, one of your shoes off, keep one on, and you start walking, inevitably you'll have some gait asymmetry, obviously, right? Same thing with mass distribution. So if somebody puts a lumped mass on your ankle, okay, you're going to walk asymmetrically, okay? Injury, obviously, if you sprain your ankle or anything like that, you walk asymmetrically. Prosthesis is one of the big parts of this. So if you have a prosthetic leg, transfemoral or something like that, right, and you have a healthy leg, if those two legs don't match exactly with the mass distribution, the spatial parameters, even things like stiffness or like the springiness that your ankles give, if those two don't match, the healthy and the prosthetic, you'll have a gait asymmetry. So there's a lot of research done on making prosthetics really same as the healthy leg. Okay. One more thing that can cause asymmetry is disease. So if you're experiencing a stroke, somebody's experiencing a stroke, or Parkinson's disease, cerebral palsy, or something like that, they walk asymmetrically. Okay. Particularly if they develop a stroke, they can develop things like hemiparesis, which is the weakness of one side of the body. And if that becomes more extreme, it becomes hemiplegia, which is the severe paralysis of one side of the body. So a person might be paralyzed just on one side of the body, just limping along or dragging their foot or having really stiff upper limb motor movements. And how do you fix that? What is the common way to fix hemiplegia, right? So one way is classical gait rehabilitation. That's the most common, most well-known, most applied. That is when a physical therapist customizes exercises, customized exercise for patients and guiding them through the motions, okay? One is robotic devices. Now, when the World Cup just opened, if you paid attention, they displayed this awesome exoskeleton, right, that can help people walk potentially, right? Tiagi loves exoskeletons, everybody knows that. And so they can help people walk, okay? So here's an exoskeleton that can help rehabilitate people just by doing the motions for them, like that will come up. I've included pedaling devices just because they're very effective in people that are not able to walk and not able to do any of these robotic exoskeletons, things like that, are bedridden, that just suffer from a stroke. So you might use pedaling devices with resistance to rehabilitate early on. And I also included that because my sister's watching on in Germany, and she's the salesperson. She's a salesperson for this company right here that sells pedaling devices. This is a little bit of a plug, I guess. So also split belt treadmills. I'll talk about that in a second. And this offers reduction of cost therapy because you can automate it. You can make it cost. You can have a certain setting for a certain patient. You can do data acquisition. So a robotic device that you have at home or in clinic might tell the therapist, okay, is that person doing enough work? Are they rehabilitating, and so on and so forth. So you can use this data acquisition to do some kind of evaluation, okay? And also last, functional electrical stimulation is when you put some electrodes on somebody's muscle and they contract and loosen, okay? You control their motion. A lot of times drop foot, which is the condition when a stroke patient cannot lift their toes and drags their foot. A lot of times they use functional electrical stimulation to help them lift the toes just by attaching electrodes to the calf, okay? So which one works best? All of them, a combination of all. And it is not just a black and white issue, okay? So depending on the severity, depending on what causes the gait asymmetry, you might apply different ones. So you might have split belt treadmill with a therapist helping the limbs, or maybe just a combination of all. So that is the consensus of research. Two things that are really important: early treatment. So as soon as the stroke happens, as soon as something happens, you have to get rehabilitation as soon as possible, like to relearn your motor skills as soon as possible. And it has to happen as often as you can. Just like in anything else, if you want to learn or relearn anything from staying in shape to a musical instrument, you have to do it a lot. Same thing with rehabilitation, right? So you have to do it constantly. So to summarize that, I just put this sentence together just to summarize it. The body is an extremely efficient, adaptive learning machine hungry for regular and challenging training, meaning that it has to be regular, and it can't just be something that you've already been doing and good at. You have to do something that's slightly challenging. That is true for gait rehabilitation. So that's sort of the background for that, very general, right? So let's jump into the gait enhancing mobile shoe and how that ties into the rehabilitation of gait. Okay? So, as I was saying before, the split belt treadmill is used to rehabilitate walking, asymmetric walking patterns. But what that basically is, if you see here, you have two threads, split belt treadmill. This one right here is in the IDR building that we just got, and this one is Dr. Kim's in Dr. Kim's lab over there. And basically, it's two threads going at different speeds. All right, so you would have the impaired leg on the faster thread, exaggerating the motion, helping the patient out to step correctly, okay? So, and that has been shown to be effective and used a lot, okay? What's the problem with that? Why is it not the magic bullet? Why is it not the magic pill for gait rehabilitation? Well, if you don't have one of these in your living room, it's hard to do it every day, all the time, okay? If you don't have a therapist, don't have something like this available every day, it's hard to do it every day. Also, the learned motions are not well retained. So if you use a split belt treadmill and you're on it for, let's say, 5-10 minutes, and you learn these motions on the stationary split belt treadmill, and you step off the treadmill, those learned motions are going to persist for maybe 10-20 seconds before they wash out. Okay. Now that is a good indicator that a prolonged time of split belt treadmill training will help gait asymmetry. Okay. It is hypothesized that this problem is considered a problem of context awareness. And that's a foreign word to some of you, but a lot of you have experienced context awareness. And that is, for example, if you're in an airport and you're walking down the airport and you see an escalator that you think is moving, but in actuality it's not moving. So you step on the escalator that you think is moving, and you prepare your whole body unconsciously. You don't even think about that for the escalator to take you forward. However, it's not. So when you step on it, you get this unbalanced, weird, awkward stance. Okay. So that is a problem of context awareness. Same thing here. So you thought it was moving, but it's not. So your body was learned, your whole life learned that this is what it's supposed to do. Okay. So same thing here. Okay. There's this disconnect between the stationary treadmill and overground walking. So given that, what can you do? Given what I just said, what can you do to fix that? What can you do to make it better? All right, to get rid of this context awareness problem, but still keep split belt treadmill. Well, that's the idea of the gait enhancing mobile shoe. Okay, on top is normal walking, like I showed before. On the bottom is walking with the gait enhancing mobile shoe, and the blue highlighted region is where the shoe would be worn. So if you step on the hill, So if you step on the heel right here, and you go through and it pushes the foot back as a split belt treadmill would do. However, with overground walking. So you're eliminating that disconnect between walking and stationary that you have in the split belt treadmill. So again, here's a sentence that I said before. The body is an extremely efficient adaptive learning machine hungry for regular and challenging training. And that is exactly what the gait-enhancing mobile shoe solves. Regular training, because potentially you can use it over different environments within your home. So if you could use a split belt treadmill 3 or 4 times a week in the clinic for 15, 20 minutes, you may be able to use the shoe, let's say 7 times a week for 45 or an hour each time. Okay? So you get more regular training. And also challenging because it does the same thing that a split belt treadmill would do. Okay? So that's the idea of the gait-enhancing mobile shoe. And before I started this research, there was already a gait-enhancing mobile shoe prototype designed and tested. So this is how it works. When the user steps on this wheel, it goes up this rack and pinion and pushes the foot backwards. Okay, this is what it looks like right here. So it kind of pushes it backwards, and it's kind of like a sliding motion. Very quickly pushes the foot backwards at each step. And here, coming up is a motion tracker. So you can see it's kind of like a sliding motion. Okay? So it was very inconsistent, and you had to think about how to use it. Okay? So it wasn't like a split belt treadmill where you can just simply not think about what goes down here, but here you have to think about your balance or losing your balance. Okay? So I came in and I said, okay, let me try to redesign this design. But this time, try to do it in a controlled way. Okay, instead of the jerky thing, I want to be able to control. So this is what happened right here. This bulky box, really bright red looking thing with funny shaped wheels. So those wheels, the reason we picked those wheels is because if you step on them, so if this is your weight and you step on the wheels, this little offset, because there's a change of radius, will cause the whole thing to rotate. And so the whole thing is passed. Because there's so much force when you step on a shoe, it's hard to control that with actuators and motors, because those actuators would be huge to just control that motion. Back then, when I was designing this, this was my approximation of the force that it would push back. So if you step on this wheel, this was my approximation of how much force it would push the foot backwards. Okay, I have to accent approximation, which will come. I'll explain later why. So this is what it's inside. Now all this stuff.
Ismet, can I ask you a question?
Yeah.
On that slide right there. That's the previous slide. You didn't include a horizontal force from the leg?
No, this is just an approximation of the force being straight down. So stepping on the wheel straight down. Now, if you include a horizontal forces like stepping this way, that would you just subtract or add it to the horizontal force.
It's a simple addition of force.
Yeah.
Okay.
So,
right.
But this is the assumption here is just stepping on top of the shoe. Okay. Like I said, approximation. I'll explain here in a minute. So this in here.
Can you go back?
Yeah.
So what is this FH average? What are you doing there?
Okay. So the force weight is FB. Okay. The FH is a horizontal force. I probably should have said that. But for right now, as far as right now, it's not very important. The important part, and I'll explain that in a minute, what all these terms mean and how to improve that. For now, this is just an approximation that tells me the average force around it, assuming that it's linear, which is not, is that. Okay.
So what is that R, theta, R, minus R, theta, F?
This is the initial radius, this is the final radius. So if you integrate from here to here, and you divide it basically by the radius, you take the integral, you'll get
Divided by the change in radius?
Divided by the change in radius, right? The whole thing. And if you divide that by that. So you're saying, so this will be your average force.
Okay, so look at the dimensions of the equation.
So you have
Force angle divided by
so
distance.
you're going to get force angle divided by angle, or divided by distance. No. Wait, right?
You have a force times an angle divided by a length.
Yeah. It might have been wrong. So, but I think when I was doing it, it was a very rough approximation. Okay. And now, like I said, I'll explain that in a second.
No, it's rough, but it is inaccurate.
Yeah.
Dimension.
No, I see that.
Not inaccurate, it's dimensionally consistent.
Yeah.
What I did when I did design it, I used this equation. I numerically went step by step. So I went at each angle step, I used this equation. At each time, I derived this. This is just an auxiliary thing, is saying that I just approximated the average. Okay. But what I actually did, I took the numerical step by step at each step of this equation right here. So,
And what is the first equation? Theta.
this defines the shape itself. That's the Archimedes spiral shape that it defines right here. So that curve in polar coordinates is this, with the initial radius and some constant and some n that you pick that will give you this curve. Okay. So, and looking at the units, Dr. Perdita, yeah, does not work out. But here in a minute, there's a happy ending to that. Okay. So, inside the second shoe, there's all kinds of stuff. The whole reason you have all this stuff in there because you take that torque that's applied on the wheels, okay, gear it down to make it a really little torque that you can stop it. You can control it with a magnetic particle brake. And the whole thing resets. So here's a video of it. This is young me, late at night. So kind of controlled, but too heavy, too tall, and most of all, too unreliable to use on actual patients. Okay, great learning experience, but it's a stepping stone in research. So I said, you know what? Let me design another one. But this time around, I wanted to make it lower to the floor. I want to make it much lighter, passive, simple, and reliable. Okay, so. But this time around, something changed, right? So instead of sending things to the machine shop, all the time for 2 weeks at a time, right, and getting it back, modifying, we had some more prototyping equipment, like this laser cutter. And I wanted to have in the chemical equation in my dissertation defense because one of my buddies, Dino, is watching. He's a chemistry Ph.D. like that. So that's they are in plastic, okay? So I had that prototype. As soon as I got that, I designed this in like a day. Built it in like a day, stepped in it twice, and said, no way, I have to design another one. Right? Did not work too well. So I designed this one right here, which is the third heat-enhancing mobile shoe. It has this little swivel up front to conform to a toe-off. Also has the Archimedes spiral wheels. And again, back then I did not have a good definition of them as far as forces are concerned. And it was 2 inches off the ground when you stepped on it. It was 3.3 pounds. And used the wheel with the Archimedes spiral equation. And this is how it works. It was really simple. It had 2 unidirectional dampers, meaning it would damp in one direction, but not in the other direction. So when you step on it, it would dampen your backwards motion with the sized unidirectional damper. And then when you step off, the springs would reset the whole thing for the next step to come. Okay. So here's how it worked. So you step, kind of pushes you back. And there's a lot of force going on there. Those dampers, if they weren't there, the whole thing would just come back really fast. So using the motion tracker and RRT over there, the infrared tracker, we measured the kinematics. And it moved back 7 inches on the average and had a fairly constant backward force, okay, of around negative 0.5, meters per second. Okay. So we did an experiment. Said, okay, let's see if it generates any after effects. Okay, in healthy individuals. If that happens, that's a good indicator. You can do it with people with asymmetric walking patterns. So we had 3 subjects. Okay, 3 subjects were measured on baseline to see if they had any gait asymmetry prior to this. Then the gait enhancing mobile shoe was strapped to their leg, to their foot, and they walked with it for 15 minutes down the corridor back and forth. Then after that, we measured the post-adaptation when they did not have the gait-enhancing motion shoe as soon as they took it off. We did that with Dr. Kim's gait right now. And then after that, they walked around for 10 minutes to see if those after effects will persist, or are they going to be washed off? More likely so. So here's what we got, okay? So this is 3 subjects, different colors, right? Subject 2, this is right after they walked with the gens, right? Subject 2 is exactly what we wanted to see, right? Oops. Subject 2 is exactly what we wanted to see. With retained after effects, and after 10 minutes, washed it off, okay? That is after 10 minutes of washing, you'll relearn it, okay? Subject 1, also good, had good after effect, and then after 10 minutes, went back. Subject green had after effects and then washed off. Subject 1, on the other hand, completely different what we wanted to see. Actually went the other way, okay? And the reason we hypothesized when we were watching the subject, we told them to walk as normal as they can, meaning going forward in a line. However, one of the subjects was kind of compensating, compensating by swinging around, and that caused all kinds of after effects that you could not predict. So here is, so after that, after the fact, we thought, okay, if we had one shoe pushing back, what about a second shoe going the other way, the same distance? So doubling the doubling the difference of movement. Okay, so doubling maybe the after effects. So this is what it looks like. It was really awkward, right? And we did some studies. That's William, but we did some studies with that. We sent the shoe up to Moss Rehab, where Aaron was doing some studies. Aaron Mendezeven, and there were some after effects in double support. However, it was so awkward walking on that it was not very reliable. Okay, so that is the gait enhancing mobile shoe. Okay, and I'll get back to that here in a minute. How this ties on and everything. Right. So that gait enhancing mobile shoe served as an inspiration to something else. Right. So let me tell you a story how this came about. So there was that wheel shape that this approximation was not really right. It was just an approximation. And for years, we thought we can linearize the force, meaning somehow have a shape where the force is constant coming back. Right? And so I think there was an undergrad that tried it, Laura Karp, this was 3 years ago. She tried it, didn't do it, went on to law school. I don't know if it was for that. Then, 2 years later, Woody Brink, I thought he was going to be here. He came in and he had a class project, and Dr. Reed said, well, why don't you try to give him the wheel shape problem? Maybe you can figure it out. He's a smart guy. Right? So I explained it to Woody. So we went back and forth, me and Woody, trying to solve it. And then one night I tried this to help him out. Right? So I tried approximating or assuming the solution and solving for it. And I assumed different solutions as far as the final shape, given Archimedes spiral, logarithmic spiral, all kinds of spirals that I assumed. But result, if I wanted a force, the force that I got out was completely all over, and the shape that it resulted from was way off. So one of the nights I sat down trying to figure it out, and I just took the qualifying exam, and I had this big stack of notes of differential equation stuff, right? And I looked through it, and there it was. You know, I was able to solve it. And that resulted in the kinetic shape. Okay? And I want to go out of order to make you see what the kinetic shape is before I go into the math. Right? So here is a crutch with this weird looking shape. Okay? So if I let go of this crutch, it rolls by itself, right? Where a regular crutch would not do that. Okay? So because I'm putting a force, the weight of the crutch on there, it reacts by having a force that's parallel to the ground, okay? Just by the change in radius. Now you can change that radius. If you have a more change of radius, this would be faster. If you have less change of radius, like this one, okay, then this motion will be slower. So there is some kind of function or control you can do, you can adjust of how much it rolls, okay? explain that in a minute. So here's what I did, right? So I took the real shape, the curve in static equilibrium, and found that there's an angle that relates the force coming down and the force, the reaction force, with an angle right here, okay? At the same time, you can define an angle that defines the radial and that defines it between the radial and the tangential to any point of the curve. That's called a polar tangential angle of the curve. And that is defined by that. So that night I was like, okay, let me set those equal. Let's do that. So I set them equal. I used separation of variables, very basic procedure in differential equations. You separate the variables, you solve for it, you get this equation, and then you get this, okay? And that is beautiful, okay? Now what does it mean, right? What does this mean? So basically, this says if I have two functions, if I specify as two functions, one, the force that I'm applying to this shape, to the radial shape, and two, the force that it reacts, okay? So if I apply a force on this shape, the force that it reacts on the ground is this. So you specify these two functions, any functions, right? And you get a radius that defines the shape, okay? So if you specify, let's say, a constant function here and some variable function here, this shape will produce these functions. So after some looking up, what am I going to call this? You know? So I Googled it. It was a kinetic. There's a lot of forces involved. Kinetic. There was a band. Kinetic shapes. You know. I was like, all right, that sounds good. You know. I don't listen to them, but nothing else was called that. So I call it a kinetic shape. This specifically is a two-dimensional kinetic shape.
What is FR again?
FR is the reaction force to the ground. So if I didn't bring that picture. Can you bring? No, don't worry about it. So if I press down on this, you have this FV, right? So that's the force straight orthogonal to the ground. FR is the reaction force that this wants to roll with.
It's a horizontal force.
The whole horizontal force, yes.
So same thing you were calling FH before?
Yes, the same thing. So it's this right here. Okay, so FR, I'm calling it radial force. Back then I used to call it the horizontal force. I should have looked at that.
Are you going to call it something else later on?
Maybe. Magical force.
So it's related to the 3D shape when you get to it.
Right. So the reason I renamed it because there's more terms on it. So if you do the reverse, this is sort of kind of auxiliary equation. Okay. So if you do the reverse, so let's say you already have some curve, some shape, and you know how much force you're applying to it. This reverse equation tells you how much reaction force you get. Not as impressive as this.
That's not consistent dimensionally either.
This one?
Yeah.
You have.
Oh, this is okay.
Yeah, you got the DR on top, cancels the R on the bottom.
That's an element that you have an F divided by an angle.
Angle's dimensionless.
That's the go.
No, the angle is dimensional, so there's R and R cancels. So.
Yeah. So you get F equals F if these two cancel.
That's, yeah, I guess you still have the angle.
Yeah. Why? There's a lot of this stuff, this auxiliary equation. I think I did like a month ago for this dissertation. I probably have one of the things I probably should fix. But if you do this in reverse, you should get something like that. I'm not sure if I'm missing here something.
And what is that, the last one?
The last one
integral
is,
zero?
so yeah, I have to know that. Okay. So you have to understand, I think there's like 20 or 30% of this dissertation happened within the last year. Okay? A lot of it happened. So this last one defines, if you're defining the radial force, and if you take the integral from whatever you're defining, if it's close or equal to 0, that means it's continuous. So if it's not equal to 0, you get something like that, it's discontinuous. And if it's continuous, you get something like this, where it goes back to its initial radius. Okay. So that's the time that Harris came in. Okay, we tested this together. So how about we test these math equations and see if they actually work out? Okay, so this is what we did. Really simple. Apply the weight to the axle and measure the horizontal force. Okay, really simple setup. And this is what we got. So for this shape that's defined with this force, given you're applying 800 newtons on it, okay? Applying 800 newtons anywhere on the shape that you are, so if I apply 800 newtons here, or here, or here, the reaction force will always be 100. That's what the equation says. And when we measured it, it fluctuated around 100. However, it's all very dependent on the surface imperfections and things like that. But that was very good. Another example here, I took a piecewise function that I extrapolated with a Fourier series, okay, and made it a continuous function, this the shape I just showed. And in this example, if you're at pi over 2 right here, you would get this amount of force given applied 800 newtons. If you're over at 3 pi over 2 right here, you would get this amount of force, right? Negative, so it goes the other way, all right? And also there's a point where you really don't, you have no force at all right here, this unstable point. So you can do the same thing in 3D. So I sit down and did it in 3D. This time around, you have a three-dimensional shape, one force that pushes away from the center, and one force that goes around the center. It's kind of difficult to show in a two-dimensional plot. So the equations for that are these two. So if you're going in the radial direction, you're using these. If you're strictly going in the radial direction, this is the same equation as before. But if you have some kind of tangential force, that the rotating force, and you're going in the rotational direction, you have this right here. Okay? And can we do this in dynamics? Right? So what about if you take those shapes and you make a move? If you step on them or something like you apply force, how do they move? So this is the Newton's second law for that. And
can you go back to the you're moving too fast.
Okay, there's a lot of stuff. I'm sorry. Yeah.
So what is this model equation?
This is just the sum of all moments about this right here. Okay.
What is J?
J is the mass moment of inertia of the rotating shape. So, and J, this is one of the things that I took out of the presentation. I was defining J, and J is defined different ways depending on where it rotates. If you have to use the parallel axis theorem, or how the shape is, the thickness of it, and all this stuff. Details you can look up in the dissertation. So this is the angular acceleration of it, and this is the mass moment of inertia of it. Polar mass moment of inertia.
Isn't it? Engineers get very excited when they see equations. So maybe when you get to equations, it's a little slow.
Oh, well, okay, but it takes a long time. I swear, there's a lot of material. No. So, is that good?
Yeah. I don't know if it's good or not, but.
Read the judge. So this is the general equation that you get from that. Not very complicated. So the C and C1s are this you get with initial conditions. So you get the acceleration, velocity, position of the shape given that you apply a force, the shape function itself, polar mass of the and polar mass of the inertia. And this is defined as the polar tangential angle. And how do we test that? So me and Harris, we went in, we built this little rig that does this. Okay. So we took a shape and it pushed a mass out. So when we pressed a force on it, a constant force, it dispensed a mass, a flat. And I wanted to do this way. One, because of the resources I had, and two, because I wanted to expand the equations. Okay.
So go back again. So the bottom equation, what do you have, rho T?
Okay. This is the mass moment of inertia that I
This is the dimensions of m squared, right?
So
what is the first term, the rho T?
This is the density, the thickness, the thickness of it, and this is the function of it. This is the mass of the platform it dispenses. And this is, again, the radius and polar tangential angle. And these are defined. This is, moreover, the approximating a particle mass a distance r away instantaneously. Okay. So this is what we did. Okay. Now I know Craig's thinking over here like, oh, this is not precise at all. You know, tolerances don't match up, right? Which in a second I'll explain why this is such a cool thing, right? So we did this. Basically, it's a weight pushing down, a known weight pushing down on this shape, and then we're measuring how fast this dispenses. And this was on the Cairn system, okay? We took really care of it, right? So because it's not perfect, I had to assume a friction model, okay? And the way I derived this friction model, so this is what it looked like. But you think, okay, you can pick any friction. Well, what I did was I applied this force onto it and pulled this mass with a scale just to see what kind of static friction, what kind of moving friction I will get. And that I put into my friction model right here. So I derived this shape, okay, really big one. So this one was this big, right? So I wanted to make it really big so I had more time to analyze, right? So this shape is a sinusoidal force. So it starts off with no force if you apply a force this way. And then maximum force right here, which is right here, okay, if you apply it that way, okay? So we started off it rolling from here all the way down here, oscillating about here, okay? So when that mass comes down, this oscillates around, okay? So this is the position over here. The green is what we measured of the displacement of the mass. The green is what we measured for the velocity here. As you can see, the oscillator is kind of back and forth, and the acceleration. The dotted line is my model that I derived for the dynamic equation, right? So it's not dead on, but it's very close, considering that the whole motion was 1.4 seconds. So let's go, right? Maybe even faster than that, right? So that's how fast it happens. Now you think, okay, this model, depending on what friction you pick, it'll change, which is true. However, I wanted to make sure it's right, so I picked the same friction for 2 experiments, the same kind of friction model, and every 2 experiments. And this is one of the experiments. And it fit out pretty nicely, considering all of the imperfections that the setup had.
Ismet, I have a question on that slide. Is the green data filtered? That's the first
Yes,
question.
the green. I know that this question came up, right? So when we took three data points, three trials of this. Okay, so we did it 3 times, and we had to match the data up in time. Okay, so I matched it up with the velocity. So you have, even if you match it up with the acceleration, you would get some standard deviation about the same, the same kind of amount. Okay, so yes, it's filtered. I forgot the amount of filtering. Butterworth's filter. It's in the dissertation, I think. It's about like 10 hertz, 11, maybe less than that. So.
And then the second question is, why is that third figure, why is there a discontinuity there?
This right here, okay, that's a good question, because that friction model looks like this. So when it gets to stop, when the whole model or the setup gets to a 0 velocity right here, the friction goes way up. Okay, so the same thing happens here. As the motion of this goes back and forth, okay, so you go back, and right here at 0 velocity, that's when this happens. Okay, that's when this friction model right here gets up. The friction gets really high. The friction gets really high in this way. Does that make sense?
Yeah, it just makes me think that so then the data that you collected won't be able to show that because it's filtered. Right?
You have to, well, friction, you have to have some kind of model to model, right?
Right.
And to have the exact friction model that the data had, the actual device, that thing that we made out of some ball bearings and some linear bearings and some wood, okay? That friction model is probably very, very complicated in reality. This is a much simplified friction model, okay? So to actually do the nonlinear friction whole shebang would be very hard to do. Does that make sense?
Yeah, I'll probably come back to it.
Okay. Okay. So same thing is possible with 3D. Okay. I can't get into the details of that, and we did not test this yet. Okay. It's hard to actually test this, to have this rotating force, a motion, and also this radial motion. So in general, if you kind of zoomed out, if you kind of tuned out and kind of for all this math stuff, so this is a summary of it. So given an applied force function is dependent on the position. Okay, so the force function is orthogonal to ground. Okay, my kinetic shape equation can predict what polar or even spherical curve will result given a ground reaction force. So if you give it a ground reaction force and you give it the applied function, you will get that. Further, the kinetic shape equation, the dynamic ones, can predict how the shape is going to move if you give it a shape or even approximate the shape. Okay. So that's that. Okay. So what can you do with this? What can you do with these with those equations? All right. So one of the things you can do is you can make them more complicated. And so one shape, if you press down on it, if you press down with one force, it'll give you some reaction force parallel to the ground. Okay. Well, what happens if you take two shapes, right? So if one reacts, and then with that reaction pushes on another shape, okay? So it's kind of like a system. What happens then? How do you do that? Okay. So there you can make kinetic shape systems, and that becomes a little more complicated, but you can do some really cool mathy stuff where you can do, you can add, multiply, subtract forces. For example, if I have two shapes going this way, like the addition right here. So if you press with one force, another force, the resulting force will be an addition of the two reaction forces. If you turn them around, it would be a subtracting force, right? The same thing with multiplication and division. You can do this multiple times, okay? Depending how much loss you have in your system. And the cool thing you have, you can do conditional statements. So saying that if the force goes one way, if you define the reaction force to go one way, then engage another shape, do something else. If it goes the other way, depending on the position, then do something else. So you can do a if-then statement like in programming, right? So given that, I sit down. I think this was one of the times you guys found me on the floor. So I really thought about this and all the combinations you can do with this, right? And so I developed this notation that you can develop things like, I can't go through all of these. You can develop things like that. So something like this is a notation how you would use these systems. Okay, for example, if you have some kind of input force and a shape reacts with a spring attached to the ground, and then you lose 10%. Okay, so you have some 90%. So you lose 10% on friction, misalignment. That force goes into this shape. That also it adds force from this shape right here. Then you have all this redirection here, and then you have a conditional statement. If number 5 is greater than 0, do this. If it's less than 0, do nothing. And you can do all kinds. You can get creative, right? Depending on your system and how you can conserve those forces. You know, of course, you're going to have some loss. And right now, I'm working on. We built this nice rig to prove that, but it's really hard to keep this loss low. Okay?
But is that a Rube Goldberg system, or does it actually have a use? Like, what are the potential applications?
The potential application. Imagine if you have a design where a machine component presses on another machine component, and depending on the position of the machine component, okay, you have maybe a connection with this. Depending on that position, it might generate a force one way or the other way. Okay. Now you can also have this thing, like the whole thing being, let's say, a black box. Okay. You have some inputs and you get some outputs depending on your definitions of your shapes. Okay. So these shapes you can define as much as you want with the input forces and output forces. So let's say this shape is one of
I
these.
guess I understand what can be done. Do you have an actual problem that this will help solve?
Any problem where you need to modify a force, you can use that.
You can make an analog computer out of it.
You can do a force computing, right? So that is the cool thing. So you can use forces to do some kind of computation, given that you have non-substantial force losses, okay, due to misalignment or friction, something like that. Is that?
Yeah.
Okay, so what can you do? Another cool thing, that thing over there that we brought in, kinetic board. Here's something really cool I thought of. So if you come in and you take the shape and dynamics, you can predict the motion of it. So it comes around, and then I'll put a little rollers on the other side. And as soon as that hits, it keeps going. So that momentum that was generated just keeps going. And you can do this in a rocking motion or even in a linear motion where you just pump your feet. Okay? So here's what it looks like right here. This is a little dramatic music. I have to shorten this video. This is like a 10-second video of how it works. There it is over there. Something like that. Okay? So the wheel turns around, it just keeps going. Right? It's me, Harris, and Norman that we were working on this.
That's your Kickstarter campaign?
Should be, right? Should be, right? It's a pretty fun little project. It's one of those side projects I really enjoy. You know? So, but that's just building it, right? Now, because this is PhD dissertation, we have to analyze it, see if it works. Okay. So what we did was we put Wii boards on top of the kinetic board to measure what forces are you applying on it. The problem with Wii board, you can only measure orthogonal forces, okay, which is enough for us, okay. So using those equations and that friction model, plugging it in, this is what was measured. This is the velocity of the board, this is the acceleration of the board, velocity of the board, position of the board. And this is when the real wheel rolls and the front wheel rolls, okay. The dotted one is my prediction, okay. Close, not perfect, but relatively speaking, with all the inconsistencies, satisfying, okay. So that's the kinetic board. Also, you can make music with it, right? This is great. If you've ever been to the lab, there's a couple of guitars. I love this, right? That's probably where this comes from, right? And how can you make music with strings? Okay, one, you can make them different lengths, right? You can, like in a guitar, you change the fret. Two, you can change the tension, right? So you can pull on a string more and less. Three, you can change the thickness of it. Thicker strings will vibrate less than thicker strings. And this is it. So because you can exactly define the reaction force of the shape, you can make it pull on a string. So depending on what position you're at, okay, using this equation that takes the string equation with the kinetic shape equation, you get this big, nice, fancy equation that defines the length of the string, the linear mass of the string, the first note that you wanted to generate, okay, and the last note that you want to generate, okay, and also the weight that you're applying on top of the force. Given that, you get something like this if you pick your parameters right, okay. And when during testing, this was what we're supposed to get, and this is what I got with little adjustments, right? And I'll show you how it works right here. Probably better said with a video. That's yellow submarine. There's a force, constant force on top of the shape. It's attached to a smoke in the water, but you see it going vroom, vroom, right? So that is just one shape, using one shape, right? So just imagine having 5 or 6 shapes in a row. When one is plucked, the other one repositions. You can have continuous music and all this stuff. Really cool thing, application of the shape.
That was supposed to be yellow submarine? The one before?
The first one, yellow submarine. But the acoustics are not this good. If you put really nice amplifiers and everything, I think it would sound much nicer. Okay? I think so. That's just proving a concept, which was very exciting. So, this right here, this yellow submarine. So, you can do crutches, right? So, like I said before, those crutches make things more efficient. That means if you step on these crutches, they can push you forward, right? So, this was a great thing. What I thought was, this is it, right? So if you step on these crutches compared to regular crutches, they can push you forward. If you're applying a force on top of them, they push you forward, like with the reaction force, depending on what kind of foot shape you have, or what kind of crutch shape you have. And we're still doing some data analysis. We're still doing things. So yeah, I can't show you the things that I got, but I'm hoping within the next couple weeks I can put it in my dissertation.
So if you're going down the slope, do you want this kind of crutches?
No, you don't. Well, you do, but then you turn the crutch. Let me get it here. Then you turn this crutch around. So if you're going up the slope or even a level slope, so you want it to assist you. Okay. So when you press down, it assists. Okay. But if you want to go down a slope and you don't want to go that fast, right? So you turn them around and they can resist. Maybe make a controlled descent down a slope. Okay? And the cool part is you can get creative with this. You can make these shapes time dependent. Make these. I don't know if you did you raise your hand?
Well, I'm wondering why you think it's necessary. I know it's an assist device, but why is it necessary to help to moving forward?
Because you use less energy. So that's reason by itself. So if you use less energy, you get exhausted less, and you go longer distances and all the above. And you can, like I said, you can get creative with these. You can make these time dependent, as far as you can change a shape in real time. Let's say you're going with a crutch that has a time-dependent shape. It might change the shape depending on your dynamics. Okay, how fast you're going, how slow you're going, how steep the hill is, and all this stuff.
How would you do that? Time dependent.
So you would take inside the shape. You would maybe have some spokes that retract and go in, maybe with some lead screws or something like that, where you take the shape and you kind of change the rim where it makes a different shape. So that's a crutch.
So Ismet, if it uses less energy, why wouldn't you create a shoe that propels us forward? It seems like it uses less energy to accelerate.
Yeah.
But for steady state walking, you're still gonna have to break that speed increase.
So you speed increase.
I think one of the reasons, I think that's the point. We are, as a physical therapist, we are helping the patient. I'm talking patient population. Providing an assistive device. Energy is one of these things you have to consider. However, I'm more considering the safety. How are you going to prevent if you're moving forward? So then I'm thinking, well, we have to test how that can be, doable, or is it actually helping?
Yeah.
Because we have tested, you have been testing a normal subject.
Yeah.
With these processes, because you have proper body mechanics, but those have like amputees or have the ACL injuries or broken legs, and this totally different story.
Yeah, well, that is a subject on its own, right? So the safety and how to customize this. But as far as the crutch itself, you can, any of you, if you guys want to, after this presentation, try the regular crutch and this crutch, you can try it. But as far as, you can see the difference and judge for yourself. But as far as the safety concern, I don't know. So I don't know the exact details of human trials and what somebody would prefer and what is more safe and things like that. So that's hard for me to say because we haven't looked at that. We've only looked at how it works and if it works.
I guess my question was, there's a reason why legs break in the first half of stance and then accelerate in the second half of stance. If you take away that braking and you're only accelerating, at some point the healthy leg has to do all the braking, in which all the energy that you gained from the previous step is gone from the braking.
Are you talking about shoe soles or the crutch?
Well, the crutch, either one.
Okay. So with the crutch, it's a little different than walking. Okay. With the crutch, the mass is different. So if this, let's say, is minimal mass, and it's rigid, infinitely rigid, made of metal, something like that, then that point, that forward swing would equal the energy, that acceleration of that forward swing, that's what I'm saying, right? Would make up the energy that you're saving. Is that what you're saying? I think if that's true, I don't think that holds true with the crutch. As far as walking, if you have this shoe sole, that's a little bit different story.
I guess I'm saying with the crutch, it sounds like you're taking away the braking that happened in the first half of the step.
Yeah.
And it becomes all forward acceleration.
Right.
But people don't want to be accelerating the whole time. People want to walk at a constant speed.
Well, you can adjust that. So if it goes too fast, so a regular crutch with a point foot doesn't do anything. But
it does. But it mimics the braking and acceleration of the human leg.
So I think you're thinking about the crutch as in like as soon as you put it down, right?
Right.
It goes,
propels you,
right?
Right.
But it is once you use it. I don't know. Have you ever used it?
I did, yeah.
Yeah. So once you use it, you can customize how much force you put in, as far as how much you're pushing off, and where you're pushing the crutch, or where you're putting the crutch. So as far as there's still that braking force, but then there's this additional downward slope that mimics a downward slope as you're going down. So that would be the same thing as taking the regular crutch and using it on a downhill. And when you're doing that, people are still able to do that, okay? And much easier than on level ground.
Well, we have to take a fulcrum here. So, the regular clutch, when you landed on the place on the ground, that's your fulcrum. You're not going to move. Probably 2 centimeters maximum.
Yeah.
And then you lie on that, and patients lie on that, and then you just swing through it.
Yeah.
Okay? And then now you're changing the location of the.
Not by much. Not by much.
Yeah. So then, how that affects the stability of the placing? Because you most like Well, I mean, it's kind of a lot of different.
Yes. Those questions are yet to still answered. However, what I can say about the crutch is that the shape. A good part about the shape is no matter how big it is, so you can have a shape this big or the same shape this big, right? It will act the same because it's a change of radius. So if you're talking about that moving contact point that you're talking about, right, is moving too much, maybe you want to use a little shape, right? So that is what the problem that we're running into right now. We use one of these big ones, and with these big ones, you have to step up higher. So you're kind of gaining energy, right? So what if we make this little, but the change in radius is still the same? It still reacts with the same force. Does that make sense? So if you're worried about that contact point moving too much, maybe a smaller one. But as far as the effects, how patients would react, how something like that, I have no idea. So that's still up for research. This is also up for research, but it's an idea. So having these walking boots, there's all kinds of these. There's cornery ones that when you use, it's really hard to walk in. There's some rounded ones that you use, maybe also hard to walk in. But what if you can change the shape, customize it to how you want to step? Okay, so that's a possibility. And also a big one is prosthetics. Right? Tiago can tell you when he was doing his master's thesis, his was a transformer prosthetic, right? So before, what happened? He used some shape that looked right, did not work well. And he went in and used a kinetic shape with some reaction forces that he specified. Beautiful. What beautiful, isn't it? Right? And that's what he's using right now. So changing the shape that we roll over, the rollover shape that I talked earlier, may change the dynamics for the better or even customized. Okay? So that's the kinetic shape. And application, we're going back to the gems, right? So how about doing that for the gems wheel? Back 2 years, okay? So we'll make a complete circle defining the wheel, given some assumed applied forces, vertical forces. You have some reaction forces from the foot, okay, as you step. And then this whole thing will equal one constant force backward. Okay, so if you apply the shape equation, and right now for the gems itself, it came a long way from that first boxy looking thing. So right now we licensed this patent to a company that came up with this. Kind of similar, I say it's kind of still has a swivel, but this time the dampers are off and the shape, the changing of the shape kind of is used instead to regulate the motion. So, passive dynamics, okay? So, passive dynamics is when you have something that has no energy, so does not require any energy. So, particularly this method right here that we developed is a generalized way to match two systems, okay? These mathematical equations can match two rotating systems as far as one, let's say one pendulum rotating, then maybe a plate, a book rotating. You can match those two with these systems. A lot of motion matching has been done with coupled systems or even controlled systems. So having some kind of algorithm and control, or even just having some direct coupling with them. But however, uncoupled motion, as far as two separate systems, little research has been done in that, okay? So that's what we're looking into. So this is a rotating system, very generalized, okay, with n degrees of freedom. So you have one, a rotating disc, attached another rotating disc. This is a chain, open chain, and that could represent a seesaw, that could represent a split pendulum, a cam, or even some continuous system. So you can make this represent any of them, making a lump system analysis. All right? So for this method, right, this generalized method, to match two systems that are not connected, you need three things. You need them to be the same degrees of freedom. So you cannot match a single pendulum and a triple pendulum and move the same. Just not possible, right? Same degrees of freedom, same applied torque, meaning the friction has to be the same. If there's a motor attached, it has to give the same torque and the same initial conditions, okay? So maybe the same angular velocity or the same position. Given that, next thing you do is you represent the model that you want to match as point masses along the massless lengths, okay? Just like you represent it as this. So do those two systems. Then you use things called kinetically matching coefficient. This is one of those things I can't get into details. The math is awesome, but cannot just show it. But in the end, so here's an example of three different systems. They're completely different with different mass distribution matched with those equations. Okay, so they move the same. Even more, there was a double link in here. Okay, so this is a single link. And even more impressive, nonlinear system, highly nonlinear system, and complex system, like a double pendulum can be matched. And even an infinite pendulum, in theory, can be matched with these equations, which is pretty cool. So here's a double pendulum, at least. And these are complete different systems, different weights, different mass distribution, and everything. Okay? So moving the same. So what can you apply this to, this method that was developed, right? So you can apply it to machine parts. If two helicopter blades or vanes have to move the same, but they're completely different, they're not interacting with each other. And you can also make them, like, use it as a good guide to match human limbs as far as swinging arms. Let's say you have one prosthetic on one hand, on one arm, and a healthy arm on the other side. Okay? If the prosthetic weighs different, if it is different lengths and something like that, you will have an asymmetric walking pattern because you can't swing it the same. However, with these equations, you can add or remove different masses from the prosthetic to make it swing the same. And you can do it with legs. However, with legs, it's a little more complicated because you're experiencing a collision when you do that. And with that collision, that changes the dynamics. And right now, we're working on including collisions into the synchronization of two systems, meaning being applied to human walking. So right now, you could use this for arms or even fingers, right, to move the same, to feel the same. So that's kinematic synchronization. Here's a fun one. This is many nights just in front of the computer trying to figure this out. What's a passive ion walker? And Craig can tell you this. These are pretty awesome things, right? He did this for his master thesis. So a passive ion walker is an entirely passive robot walking down an incline with human-like motions. So a passive ion walker over the years has developed from a splitless wheel to a compass gate model to a 3-link model and maybe an asymmetrical model. Okay. So there's a lot of studies done, right? So these are all the studies I could find about passive ion walker. And mind you, that's passive, right? So that's no actuation, just down and around. So there's a lot of studies with compass gate point foot, some here with ground reaction forces and human research. And there's some with a curved foot with constant radius. There's a lot of those. And some that use in human research here. And some that have different shaped feet, right? And the asterisk means that the different shaped foot was just a flat foot. Okay, so there's a lot of those. 3-link models has been done a lot. Craig did one of them. Asymmetrically, human research and things like that. With a curve, some of them. The green part is nothing has been done, right? So nobody has really attacked that or done anything. So these green parts is what I solved with my model. Okay, so I'm filling in these green parts with this thing right here. Okay. Now again, I can't get into the details. Trust me, you don't want to see it. The details look very ugly. So here's only a part of 1/4 of the walkings of pattern. So this is the equation generated by a code to make the walker with different size feet, with different variable feet, do what it's supposed to. It's a great screensaver, by the way. You know? So I can't get into the details, but this foot can be approximated depending on the velocity of the walker, depending on the position of the walker. So all kinds of continuous functions you can fit to this and make it see what it does. So it's very versatile. Okay. So we use that walker to do some things. Let's compare it to human. Right? Just the forces, the reaction force to human. You can see it approximates. It does not have a dorsiflexion, which is the anklexion, right? So that part will not be shown. But as far as the other trends, the trends look pretty similar. Okay. The dynamics of it, right? How it moves. Okay. So this is human. This is the passive ion walker. Okay. And split belt treadmill. Can we put the walker on a split belt treadmill? Right? Did that. So this is the split belt treadmill, and this is its counterpart of the walker. Right? It's a little different. Okay. But when we get to the GEMS, going back to the GEMS research, you know, it gets a little better. It gets can approximate it maybe better. So the walker cannot probably use for exact prediction, but as far as approximation, it has some future in that. Here's a cool one for that rollover shape that I modeled, right, for the walker. This is a study done for human troughs. So what they did was they attached a radius shape onto humans, right, and they see which one is more efficient. And the radial, this is the ground reaction force and what it does, and this is my model right here. Same kind of things. Interesting part is the greater the shape, the greater the radius is, the more it applies, the more it gets to continuous rolling. So the bigger you make that foot, the more it becomes just a wheel rolling down with a constant drag. Right? Same kind of things, right? Here's a really cool one, interesting. This is the curvature change. So no curvature, a lot of curvature, right? Something that the crutch would be, right? So this is its walking energy, okay? Normalized walking energy per step, right? So normal has some energy, but the more you go into this, the more you exaggerate this, the more energy you use. And I use different types of ramps to see if there's a pattern pattern, okay? So this is more energy. Now going the other way, if you change this the other way around, I couldn't do that, okay, because the walker would fall over, right? So there is some stability issues with the walker going down ramp, and it's a big constraint. But however, it can predict some things and some trends like this. So that is a pretty cool tool to use in human dynamics and what can be done with rollover shapes, and even masses, mass distribution, approximation of prosthetics and things like that. With that model, I used to do some psychology, right, which is really weird, way out of my comfort zone, right? But this has some psychological aspect to it. I did a study with the uncanny valley. Now, what's the uncanny valley? The uncanny valley is basically that reaction you get to something that almost looks human. So, for example, like a robot guitarist right here is normal because you know it's a robot. Over here, Abe Lincoln giving a speech that's also a robot. It's kind of weird looking, and it generates this weird feeling, okay? Well, there's a plot for that, okay? This is from a study back in the 70s, right? And this has been carried over for a long time with prosthetics, with animation and things like that, okay? So industrial robot is not human-like, not very human-like, does not seem human-like. The more human-like you get, like the Osmo robot, Petman for Boston Dynamics and things like that, you get more familiar human. But right before you get to really human, healthy human that seems human and is human, you have this big dip right here where something is almost human but just feels weird, like zombies or something like that, or just a weird walking pattern. Well, that's what we looked into. What can you do to a walking pattern that looks, how much can people perceive a pathological walking pattern? Would you be able to perceive a walking pattern if the knee was up here? Yeah, you would think that's weird, okay? What if the knee is all the way down on the heel? That would be weird looking. But is there a gray area where people say, I'm not really sure, I think that's normal, even though it's not, even though spatially it's completely different? Well, that's what we did. And here's the video I put together of all the kind of summary of videos that we showed participants that were judged. It's kind of a little happy. So this is the Pasadena Walker, covered really aesthetically, really nice. Right? You know, there's one with like different aesthetic looks, okay? Different speeds, different sizes. We showed all these to participants, you know. There's 20 of them, right? Different rollover shapes, but I kind of highlighted the rollover shape here. Just knee location, asymmetry, all this stuff. Knee location up here. Here's one that's kind of limping one. So we just look at the extremities. What can we recognize? So, and these are some results from it, right? So we analyzed gait speed, gait height, knee height, you know, step length, step time, rollover shape. This is the results, right? Down here is very abnormal, what people thought not very normal at all. This is very normal, and you couldn't tell the difference if it's normal or not, right? If you change or neutral, where you really doesn't really matter, you know, they couldn't tell anything. So for the knee height specifically, it was pretty interesting. If you put the knee 83% asymmetry of knee height, so one really high and one is regular, right? You can tell the difference. Same thing with the knee really low, right? But there is a place, there's an area here where you can have some knee asymmetry as far as the knee location is different. It's not normal, but people can't tell the difference, right? Same thing with rollover shape, same thing with knee damping and things like that, right? This gives an insight of what is possible in design. Some design constraints that you can say, okay, somebody designing a prosthetic, maybe it's better to have the knee higher or lower. And at some point, people can't even tell, although the benefits from the dynamics and the kinematic point of view are much greater by moving the knee. So that kind of gives a hint to a design constraint what is possible. So that is the uncanny valley analysis that I did with the Pasadena Walker. So that was everything, okay? Minus a lot of details, a lot of things that I wanted to put in, but just no time. Even as it is right now, I think we're way over time. 50 minutes, there was.
It's 11 now, so.
Oh man. Well, okay. So these are the things that relate together. And with this stuff, with all this stuff, I had 1 master's thesis, 5 journals, 5 conference papers, 1 book chapter. All of them was first author, except the book chapter, and 5 patents with 2 licenses out of all that stuff. So, any questions about any of that? I know maybe some of you probably have to go. Sorry, like I said, there's a lot of things within the last 4 or 5 years there. Some of them are kind of different, you know, and it's hard to hide them together.
All right, so let's start the questions from the audience. Then we can move to the committee. Any questions from the audience?
Audience, come on. You read it. You look good.
Have you considered with your kinetic shape and your reaction forces? Have you considered adding material properties to the contact surface so that, like, if you know your kinetic shape or your wheel, you know the material of that, material properties, etc., and you know the material that it's interfacing with on the ground.
Yeah.
And this gets into the friction model thing.
Yeah.
But knowing the 2 materials and their properties, you could determine what contact patch you would have with that wheel.
Yeah.
And that will determine the stresses, the
normal
stress and the shear stress on that wheel. So, for instance, when they were going to design that new iteration of the gem shoe, they would maybe want to look at those types of things when selecting the materials, when determining, what this gem shoe is going to walk. What materials could they potentially walk on, be it a wood floor or concrete or something like that. So I didn't know if you had thought of going further with the materials sense of it and also the friction model as well.
No, I don't think so. So that's a complete different realm. For this model, it's a no slip, so there's assumed the no slipping, right? However, there's this, as far as contact is concerned, I have a section in dissertation that talks about if you have some surface imperfection, it can affect these reaction forces, right? So sometimes using a bigger shape will take away those imperfections, right? From the shape and stuff. And you can also change the shape itself to get rid of imperfection. As far as the stresses and shear stresses and all this stuff, that's not within this research, and I didn't look at it. But if you're a designer and you want to use it, that's definitely something that you have to look at.
And that's where I'm looking at it from as a designer.
Right.
And those are the things that I would want to know if I was going to try to design that shoe or do more research on the shape.
Yeah.
Expanding on this question, so have you thought about including gear to keep on the rims of on the radius of the shape in order to predict the friction?
You mean like the gears? Yeah.
Like gear tooth on the so you'll have a raw track and pinion kind of deal, and then.
Way ahead of you, man. That is so. Like that same section, I devoted a whole section on the application, what to look out for, what my experience is, and one of the suggestions is you can use rubber, you can use gears. However, if you do use gears, they have to mesh. So if you have some kind of weird looking shape, you have to watch out that it has to mesh. And if the gears are really big, the teeth are really big, it might affect the reaction force, right? So if you do use gears or some kind of thing like that, make sure the gears are very relatively small. I did not look into this further, but my approximation is from the smallest radius of the shape, maybe 5% of that. That's an approximation. I didn't look into it.
What material did you use to make those 2D and 3D structures? Those things that you have?
Polymethics.
Polymers?
The chemical equation I had on there, right?
Oh, okay.
Well, it's just Delrin plastic, right? I did it for the smaller shapes, right? Now, when I did the big shapes, this would be a big waste of plastic, right? So what I did was I printed them out on printer paper, taped them together, put a template on some wood and jigsawed it out. Then really nicely, so I made this really big shape that I'm going to bring in, like the wheels of that kinetic board over there. So yeah, but I mean, there's literally many things you can do.
Yeah, I have a question. Back on the gems, so one of the first goals was to make people actually recovered gait mode, right? People who walk regular to start walking regularly.
Right.
With the kinetics, it seems to me that it accelerates too fast and stops too fast.
Yeah.
So when they get off the GEM shoe, they realize that the foot doesn't actually follow the same speed, the same acceleration of the GEM's.
That is a big problem in the GEM's design, is to control that backwards motion. That second design, that bulky one, that was all about trying to control that motion. Now this one right here uses dampers. The new one that the company is trying to design is using the shape in conjunction with a spring. Okay, so there's a lot of things you may be able to optimize on the shoe. I'm not saying it's perfect. I'm just saying there's a lot of optimization options in the way it moves, how light it is, how tall it is. You can go on and on about this, depending on your resources, depending on your experience, and things like that. But the idea, I think, is great. Sam?
Well, if there's no other questions from the audience, we can start questions from the committee. Who wants to start?
Before he asks a question, let me just say to all other graduate students, it's good to have page numbers on your presentations because now we can't. It's going to be difficult for us to direct you to slides we want to discuss. So
This is a new, this Prezi thing, yeah.
for other graduate students preparing presentations.
Yeah.
So maybe it's a good idea to give a copy of your handout.
That would have been a good idea. Yeah. But if you like, as soon as you say the topic out of those three, I can zoom in and if you want me to get to some certain section.
Is this available? Have you posted this to the web?
You want me to? This?
Yeah, so it might help some of the committee members who have laptops
Sure.
search through it.
Sure, I can do that right after this. I'll post it. I'll post the link to this presentation.
Okay. I guess I'm gonna just comment, general comments about your. I don't know if you wrote your abstract and the conclusion. Just
Last
at the
night.
end, like
Last night.
Last night.
No, not last night. Last day, because there was literally so much things that I wanted to put in, and I guarantee there's one or two sections in there that are underdeveloped, like the question.
I mean, there are so many grammatical errors in your abstract and conclusion.
I guarantee you. I guarantee it.
I can guarantee, and you will rewrite the abstract intro.
Oh yeah. Yes.
Those three sections would have completely rewritten.
A lot of the whole there's some grammatical errors throughout the whole thing, just because.
No, but the abstract is like every other sentence is wrong.
Yes. The middle sections are better, but those were done.
Yeah, the middle section of the abstract and the conclusions, I think.
If it wasn't for autocorrect, I'd be doomed.
Oh,
And
the other way.
Yeah.
Look at your thing. You toss it over correct, and you, according to that thing, you peruse your degree here.
Huh?
You peruse your degree here, right?
Perused.
Look at yeah, that's what you said.
One of the sentences, I can also be applied.
I can also. It can also be applied.
So I can also be applied.
From and form is another common one.
I mean, and you always put a instead of a in a lot of places.
Yes.
Which is to all the documents.
Like I said, I swear if I had 1 more or 2 more days, I would have revised those. But
I doubt it.
It always comes down to more stuff. It always more stuff. I know it is very true. No, you're right. You're right.
And I guess I'm not a big fan of using I throughout the document.
Yeah.
You know, in formal writing, people don't normally use that. And they don't know
It was kind of awkward because I'm used to the conference paper and journal papers. We or it was done.
Yeah.
But that's what I teach the med class 1 students always. That's how you write, right?
So you're teaching them that, and then you're
yes, but this is a thesis. This is my work, right? This is what I did.
Yeah, but this is a formal document.
Much for the reason.
Yeah,
yeah.
Much for the
This is
reason.
a formal document. And I mean, people know it is your work. You don't have to kind of overemphasize it. Like you write a sentence like, I have named my definition of these shapes, kinetic shapes.
Yeah.
You don't need to say all. I mean, you
Yeah, I
know, once
know.
people realize that this is original work, they will name it after you.
I know.
It'll be called
The way
shapes.
the way I reasoned it, the way I reasoned that is, if you're, this is gonna sound a little pompous, but like if you read like a manuscript, somebody wrote like, I don't know, back in the days, they would use that kind of language. But it's kind of pompous. I know it's a little arrogant.
That's what it makes you sound. Arrogant. At the end of the day, you say, who is this guy?
Yeah,
You
yeah.
guys didn't do
The
this.
way I usually judge this is if I think anybody doing the same thing would get the same thing, I would say it can be done. Or go with the informal if it's a math derivation that anybody should get.
Yeah.
But if it's something that where you're giving your opinion of how, then it's maybe more appropriate to say that you emphasize the I, just because someone else might have a different opinion on it.
Man, this is a lot of grammatical stuff. This is my third language.
It matters how it's read, though.
Yes, yes.
So,
and I guarantee you, me and Dr. Wu will make me do this a long time from now. We'll make me revise this over and over, even the stuff that we add. And I like to add a lot of things like the clutch data and stuff like that that's not in there. And there's some passive dynamic Walker sections in there that are not ideally developed, I would say.
May I jump in, because this was part of the thing that I was going to just think on this very same thing.
Yeah.
Do you realize actually when the more you add, the more you devalue everything that you show?
And
Because
research.
no, listen to me. Because it doesn't matter now that this is a thesis. And on there you're going to present papers or write something. And if you put so much stuff in it, people are not going to read it.
Yeah.
You see what I'm saying?
Yeah.
I mean, you want to emphasize the big things, you think are big contributions, a big part, pay attention. And then the other things that are sort of sideshows are sideshows.
Right.
Like, think about the string and the frequency and so on.
Yeah.
It really, in my opinion, takes off from the rest of the work.
Yeah. It is, like you said, but for a journal paper and a conference paper, I would totally agree. But as far as a document that documents everything you did in all the steps, I think that might be a good place for a dissertation to do that. Because a lot of times, in personal experience.
Well, I guess that's not. I mean, you don't want to get into
Right.
argument about.
That's it. I mean,
No.
It's just this is just advice, it's philosophy. You have
Yeah.
your opinion, my opinion. I just want to say that's it. There's not.
But what is? I mean, do you have a slide showing what's your original contribution? Do you create a slide?
Is it like a conclusion slide?
Yeah. What are your main original contributions?
Contributions, as in that within all this.
Yeah. If you were to summarize, what are the three things that are original?
Three things. The second and third.
Those are the three things.
Those are the three things. But I mean, it's hard for me to list because there's a lot of it that is just mine. I mean, like the Pasternak Walker idea is not mine. The Walker model itself, the idea is not
See,
mine.
one of the things I guess common in your presentation, although you showed 200 references, but there was no presentation in the beginning how it builds up on what others have done in the past. Like for example, the gate financing shoe was done by Dr. Lee, right?
Yeah.
So anyway, go ahead. So what is your contribution original on these things?
You want me to list exactly what I came up with, what I developed?
In summary, yeah. Can you just talk about it for 2 minutes?
So the first thing I did was the mobile shoe. The second and third design. First one from master thesis. That's probably I didn't go into detail on that.
So that's master thesis for your dissertation.
For dissertation, the third shoe, the testing of it, working with trying to get it to the market. Then the kinetic shape. Then the systems, the board, the musical shape, the crutches, kinetic shape in general. The passive Walker, that curved model that was never there before.
So you do say in your write-up that everybody has looked at circular shapes, but nobody has really analyzed curved shapes. Is that true? I mean, there's no literature on that?
What's the part of the background? The background.
The background, or somewhere I read in the conclusion also.
Yeah.
So there is not much work or no work on
not much
shapes that are circular, non-circular.
There's works as in like analysis. So somebody analyzing a rolled over shape.
as in like somebody analyzing somebody's walk rollover shape. That is what I'm referencing, saying that a lot of research has been done showing that the rollover shape is not constant, right? But a lot of times it's assumed constant, like that. I like that one study I showed about human trials using constant assumption of a constant radius shape, right? Looking at the vertical force, looking at the energy expenditure, and their conclusion, in a lot of these papers, conclusion is 1/3 leg length is the most efficient consensus.
What is the basis of that? Why 1/3? Why not half?
Because it's the most efficient. Like
why
that
is it most efficient?
Human studies have shown that they use like.
Is it shown through analysis or is it just from?
I really cannot cite. I'd have to look up the papers exactly what the reason is, but there.
It's like, you know, if you look at the human arm design, you can show through analysis the best way to design a human arm is the two upper arm and the forearm in equal lengths, and I guess somebody thought about that through evolution, but you can show it through mathematics. That's the best stuff.
There's some like I said, you know, there's a couple papers that have approximations, as in like their model of why constant shape is approximated, why they use it for walking robotics, why they use it for the passive land walker model, why they, and then there's also papers that look at things like they analyze it, directly measure the rollover shape and what it is. Okay? So there's also like some that approximate, then some that measure. And those two things sometimes don't match. And a lot of times you approximate simple models like that. If you would model that passive dynamic walker with the real rollover shape, it would complicate things a lot. You know? So it might be a simplification that people use to explain the efficiency of it. Okay? So, but as far as like the actual rollover shape, what happens is not constant. It is dependent on position, velocity, even your shoes. You know, like if you're wearing heels or not heels, that could affect the rollover shape. There's paper on that too.
So when you say the original contribution was on this kinetic shape analysis and all that, I mean, is that doesn't exist?
It doesn't exist. Not exist. Just now.
Any what else? And the passive dynamics?
That model with the curved foot that you can design any continuous function, dependent on position, dependent on velocity. So a changing foot, I derived that. Okay? So with a lot of coding. But that is one of the things, you know, that I added to that. Like when I showed that chart with all the research and all the green spots that were empty, you could fill that with that model.
Thank you.
Couple questions on just back on the gem shoe. Let's see here. One of the things you talked about is context dependence, and just you're creating a new context when you put someone on your gem shoe, right? And they're how different is the sensation of wearing a gem shoe from, say, being on the treadmill or ordinary walking?
I'm going to answer this in respect to the gem shoe that was designed.
Right.
Ideally, the gem shoe is very constant, very smooth, very light, very low to the ground, and you don't have to think about it, right?
Right.
That's what a split-belt treadmill is. And you're stationary on a split-belt treadmill, and if you're on it, everybody's been on a treadmill, you're just not moving. When you get off a treadmill, you get the sensation of disconnect.
Right.
But with the gem shoe, you still have the sensation of movement. So when you take it off, it persists a little better. Now, this might not be the optimized design which we're working on right now, but it still gave after effects. It still gave what we're looking for preliminary studies. Okay. So as far as comparison to it, ideally, motions same, but the context different.
Right. So one of the things I noticed on this is your experience in contacting the ground seems to be a whole lot different, in that you're
off
a little bit.
Yeah, yeah. So that you've got this height change through your stride. It's quite a bit different.
Yeah.
Especially with your red shoe, where you have the constant height, and then the other foot seems to be going up and down a lot. And I'm wondering if that's
Well, if you watch that video, I showed the second shoe. The other foot had a platform to even that out, right? So that is, like I said, ideally that shoe would be as low to the ground as possible. And the new design that company was designing was really nice. I think it was an inch or half an inch. And if you compensate for that, maybe with a thin, light rubber sole on the other foot, I think that can even out.
Yeah, so it seems like it's almost more like one foot's walking on a trampoline, and then the other, and one's on solid ground. So if you compare it to the split belt because of the height change under your stride.
Yeah.
So
that's one of the drawbacks of the shoe. So you're stepping up just a little bit, right? But considering stroke patients, right? There's all kinds of severities. There's one that are bedridden, and there's some that can almost walk only, right? So the shoe is not targeted for ones in the lower spectrum where they can hardly walk, right? You need better, more attention from therapists, right? So the shoe would be more like on the higher end where you can maybe use a cane with it, or even at the beginning with some assistance, maybe with some rails, things like that, and eventually building up to more independent use.
Can I?
Yeah.
One more question into it. So that, let me ask you this way: do you know how the stroke survivors, hemiplegic stroke survivors, how they walk?
They walk really awkwardly sometimes. With sometimes
what is most common? Okay, this is moderate, severity.
Okay. Moderate severity.
It's a little, hemiplegic circumduction gait, and then, so I'm just wondering, you understand exactly the dynamics of their walking pattern?
I think so. I'm not sure about the average. You probably have more experience about that. But as far as the shoe design is concerned, on my part, the design of it and what it's designed for, I think that given a stroke patient, they can lift their foot just a little bit with even awkwardly. I think it would be beneficial.
Well, two component you have to consider. Actually, this is very critical. So when they walk around, they are doing circumduction because they have a little push-up problem and also knee flexion problem. Okay, so that means you walk, for example, they're doing like this. They cannot push off. Then they have to they have bending toward their good side. They're circumduct. Okay, then think about landing. Landing is it's not going to be like a forward backward. It's going to be like a kind of sideways like this. And on top of that, you have to consider they're going to hit with the toes first. Okay. More than half, of them they hit forward with toes first. Right? I'm just wondering how you're going to if you toes first with the gym shoe. The dynamics are going to be the same as hitting with you have two wheels there. Yeah. And then hitting with the toes and hitting with the heels is going to be the same. Yeah. Similar.
No, it's not the same. So if you hit it with different parts of the shoe, it's going to be different. But if you can optimize it to have the wheels of different parts, not just that, have the way somebody's strapped into the shoe different. So even with the split belt treadmill, I'm assuming that you need some adjustment the way they walk onto the thread. Right? So I mean, there is some adjustability options that are offered by the shoe, where you can put the foot in different positions, have the wheels pointing in different positions, to just push the foot backward, exaggerating that motion. I mean, I completely agree. There is definitely some considerations for customizing the shoe for individuals with different severity. Okay? So, but I'm really hopeful. I mean, we're doing the clinical trials here soon, And with this redesign, the slider floats around and has some good movement, that it will translate those motions over around.
Right. It's, I mean, you can sit with, I'm part of the clinical trials, but I'm very concerned about how we can train the stroke sliders to get used to the device, especially with this foot drop things.
Yeah.
And, we have to deal with that, but I just want to make sure you are aware when you were designing this and we are. I think this is an awesome design. I really like your presentation, but the reality is somewhat different from what you were thinking.
No, I mean, ideally, reality are a lot different. When I first got here, I had the same kind of questions, right? The same kind of questions, but I think the idea is great,
Sure.
And even though there's some design issues, constraints, they can be alleviated, But as far as the idea, I think it's good and has a future.
On this, what it does for the patients, is it more psychological or is it more physical, muscle training, nerve training?
When you say psychological, you mean the learning part?
Learning a new way of walking. So I mean,
I think those two ideas are interconnected. I think you're talking about how is the motor learning, the unconscious motor learning, and it theoretically is the same as the split-rod treadmill, as in you're learning this and you're exaggerating, not just learning, but you're training different muscles and the body gets used to different learning things. Just like you would with an exoskeleton, it helps you with different movements when you're doing the learning. So unconsciously, obviously.
Well, let me interrupt you.
Okay.
More the learning perspective. Actually, I'm teaching more learning control.
Oh, here we go. Oh my God.
And because you cannot rule out. I know it's you train spiritual treadmill. They don't have to think too much about walking on the treadmill. Usually we manipulating the speed of the speed from each belt. But gym shoes is different actually. From my perspective, I mean, it requires a lot of the patient attention. Right? They have to focus on how they landed and how to move moving forward. But on the treadmill, you got to step forward unless you're going to be, tossed out.
Yeah.
But this is different. Okay, the speed is not going to be consistent, and you have to, concentrate on walking. So cognitive perspective is very important, component in terms of motor learning.
So this, just a question, if you're learning something, you have to think about it first. Right? Does that factor into that?
A very huge factor.
After a while, you do it automatically, so to speak. After a while, you don't think about it.
Once you get the skill, we call skill. I mean, you got the skill level.
But I see what you're saying. You're saying that a split-rod treadmill, you have to learn. Like, as far as if you don't, you fall. If you don't, you fall behind. But it makes you do it. Right? But if you step on the gems, the theory is that you step on it and it does the motion. Okay? But you do have to think about it more.
I just want to make sure that you have an additional component in terms of motor learning. Cognitive factors and what are the physical factors. You shouldn't rule out those additional components. We don't just let them, okay, do it. Just you hope they learn something. Because it's not going to happen.
There's a possibility of having assisted by a therapist at the beginning until it becomes comfortable, and then maybe they can do it at home with maybe a family member assisting, or maybe with some assistance with walking canes or something like that. But I completely agree. So maybe at the beginning, you would have some assistance to get the initial learning going.
Okay, moving on to a slightly different topic. It was kind of interesting when we were talking about adding some of these things, these things are a lot like cams, and now I don't know enough about CAMs to argue with you about how original this is or anything like that. But one of the things I do know is that for most CAMs, there is a linkage equivalent to them, or there can be. And so is there a possibility when you go to your series of where you're starting to do addition and multiplication, all that sort of thing, you think there's linkage equivalents of those things?
Instantaneously, yes. Every instant, every position, you can have a linkage equivalence. However, the beauty of this is that it's a continuous. So depending on how you position the shape, you'll get some force output. And you can have this as one link this way,
right?
Instantaneously. But the beauty about this is it's a continuous thing. So if you reposition it, that's a different link. It's a different link. It'll give you a different reaction force. But as far as instantaneously with the same position every time, you could represent it as a linkage.
Right, and there are ways that you can transform linkages into CAMs and back and forth. You end up
so CAMs, a lot of
removing links and adding links. Yeah.
Before, so when I was writing the journal paper for that, I did this extensive background check. I think every day me and Dr. Weir sit down individually and just look, has this been done before? It had to be done before somewhere, you know? It's too cool not to have it done, right? So we looked at it, we looked at CAMs and things like that. And CAMs are usually generally concerned with the kinematics. So kinematics and also the contact surfaces kind of thing. As if like one cam goes to this surface and does this. So a lot of it is concerned about how it moves and how it contacts with the surface. Okay? So a little is concerned about the reaction forces and the direction, and where you can customize it exactly like this. Okay? Now, I mean, there's been people in the lab that started calling it CAMs, and I'm like, no, it's not a CAM. Don't say that. You know?
Okay. You'll probably have a hard time arguing people with that, but your use of it is different.
Yes, and it's hard to explain this concept without people getting this pre-notion of that it is a CAM. So, and people are like, oh, it looks like a CAM. It's kind of rolls and CAM here. But as far as the dynamics equation, I can see that being like a CAM. Okay. But as far as the static, the forces, the force, even the dynamics equation, the way it's defined by forces, I think is unique.
So your design technique is unique from a different perspective. But in terms of kinematic pairing and how that all, I mean, you're going to have a hard time arguing with.
Kinematic. So if you take those, take those systems and you put them in motion, you might as well have CAMs.
Yeah, exactly.
One clarification that we just think of in terms of defining it that most people get through is CAMs are focused on motion,
right?
Kinetic shapes focus on forces,
right?
And if you think of it that way, they are distinctly different.
You can't have one without the other. But yeah.
You can't. But think about a CAM, like a CAM in your engine.
Right.
I mean, yeah, it's designed to withstand a force, but they don't care what the force is. Whereas here, we really care about what that force output is, and so that's the primary design objective.
Right. So it's philosophically the same sort of thing shows up in machine design or mechanism design. We focus on the motion, but if you're doing dynamics, you go from the force approach, and so it's kind of the difference between dynamics and kinematics in terms of your design philosophy. So yeah. Okay.
Well, in statics and kinematics are complementary. The same equations apply to static forces that apply to kinematics. Like in Jacobian in robotics, Jacobian transport.
Okay. One last comment. I noticed you talk a little bit about chaos. That some of these synchronized systems can go chaotic. I'd be very careful about that. I don't know if you publish anything in that area.
I concur.
Because when you say that you have to have the same initial conditions, you just can't do that when in a chaotic system. That you can't get close enough to the same initial conditions for this to work.
If you go up to degrees of freedom, you're probably right.
Yeah. Well, it's just what the definition of chaos. So as soon as you talk about synchronization and chaos, you've violated the fact you need the same initial conditions.
So a lot of this, the kinematic synchronization, the idea and the application for the lab and what we do is a lot of this application to swinging limbs.
Right, and I think you're fine there.
Yeah.
I would be very careful about trying to publish anything where you mention the word chaos in relation to synchronization.
Maybe that's what we're waiting for.
Yeah.
We're waiting
Yeah,
for
yeah.
this.
It will. People will not react well to that, just because it's. You got some.
We did look into it, and we were.
Yeah. I'd be very. I probably wouldn't let that fly. As just it ends up contradiction.
People talk about chaos when there's something you understand. The same thing with turbulence. Everything else is turbulent, right?
Right.
However, from the strict point of view, chaotic is very clear, very precise.
Right. It's different kind of thing.
Yeah.
There's a whole research field about chaos.
Yeah, we did intentionally steer clear of a lot of that.
Okay.
Okay, so this business about the uncanny valley, it's a cautionary, it's a psychologically cautionary for designers. To suggest that once you get close to human, then people start noticing what's not human, right? Flaws. I guess I don't see how that has any effect on what you're trying to do. Like I don't see how if you're trying to make a leg that looks more natural, why a person would be cautioned from making it look too natural. I'm missing.
Okay, so with the uncanny valley, it's hard to put it in gait perspective, but I think it's, if you think about, if you're out walking, say, in public, and you see somebody that is awkwardly moving with some extremely pathological gait, right? You definitely think that's abnormal, and there's this not eerie, but this uneasy feeling that you feel, right? And that is what the kind of context we look. That's the extreme case. You might see somebody that's limping, and you see that's not normal. That's the kind of context we're looking at. As far as like the uncanny valley is concerned, it is a design constraint for realistic things, as in like robots and things like that. But we're using it in context of walking.
But the valley suggests that the closer you get to natural walking, people actually perceive it to be worse.
So once you get closer,
right,
there's this dip in the valley, right, where it's really bad.
Right.
But then you get out of the valley, and it gets exponentially really good.
Right, and I can understand that related to animatronics. Has that ever been perceived on prosthetic devices?
Indirectly, I would say yes. That was one of the discussions we and Dr. Reed had. How do we frame the perception of gait? Right? How do we frame that within uncanny valley? And I think, like I said, the way we frame it is how normal, how socially acceptable, how normal it is to a normal gait. How does it feel normal? Does it look normal? You know, that's how we kind of look at it. As far as a perfect fit for the uncanny valley, I personally would argue that there could be arguments done that that's not a perfect fit for that study, but I think you can make it in that context very well. Does that kind of answer what we've discussed?
So just put it, this is a little beyond kind of looking forward to proposal advice, but it's sort of a bigger aspect of how this all fits together is if you take a gait and you have someone who's inherently asymmetric, so they have different force on one leg, different force on something. So we use the dynamic synchronization to show that if they're inherently different here, you can force and have the same motion between two different asymmetric systems, but then you end up with different forces. And so they're not truly symmetric, they still have a force asymmetry. And so can you then relax the perfect kinematic synchronization to allow the forces to be more symmetric? And then in the same process, can you then take into account the perception of a gait? And so what is So a lot of the rehab focuses on making someone perfectly symmetric.
Right.
And that's the goal. But that's not physically possible. There's always going to be some asymmetry in an asymmetric person. So relaxing it, and then taking this perception into account, where you can say, well, how much asymmetry can you have where people don't notice it? So if you have 3%, is that acceptable? 5%, 10%? Same thing with the knee. If it goes up 2 inches, are people going to notice it? No, but then you can use that to then tune the kinematics and the forces.
I think the uncanny valley is a completely different idea. You're talking about the perception goes down linearly, or there's some ramp or exponentially. But the valley specifically suggests that you're going to, as you change the knee away, there's going to be this huge, like, oh man, that really looks terrible. And then as you move it further away, someone's going to say, oh, that looks better.
Well, so one thing in that graph, I don't know if we showed the uncanny valley, you had the right side of the valley highlighted. Unlike almost every other uncanny study, we're focusing on that highlighted portion right there.
Right. So
we're looking at the coming out of and going down into.
So then that's a monotonic relationship.
Yes.
Which means the uncanny valley stuff, to me, is a peripheral that is not worth getting in. It's a distraction, in other words. You're talking about the monotonic part of that curve.
Yes.
So then.
So we're not even crossing this. We're just figuring out how to get out that valley in context of gait.
Right. But do you understand what I'm saying? So then,
yes.
The framework of the
you're saying the whole valley is not relevant for this study, but
right.
We're just focusing on the perception of.
You're focusing on a monotonic relationship,
right.
Which is. I mean, and to me, this speaks to some of the other things I read in your dissertation. It's interesting to talk about the uncanny valley, but to me, it's not useful in the context of this discussion. Because you're just talking about this monotonic trend.
But I mean, if you look at it in a way, uncanny valley is a measure of perception.
Right.
In our study that I did, perception of gait is also a study of perception. If you look at it that way, and in this context, then you would say, okay, that makes sense. But if you look at it, like you said, going into this way, taking the whole thing as a whole, then it's hard to make that argument, right?
But why this picture is interesting is because once you get close to human form, the familiarity goes down.
Right.
You're not even, that's not a part of your study.
Right.
Right?
So
the reason why this is
interesting,
interesting, right? So the reason why this is interesting and why this is useful has nothing to do with what you're doing. It's a separate.
It's
am I incorrect?
It, but as far as specifically what we're doing, no, we're not doing anything over there. And I know you're saying this.
You had just drawn a line,
right.
Just the monotonic relationship, right? And said we're trying to increase familiarity. We're trying to increase human likeness. You can say that on a page rather than describing the uncanny valley and talking about things. To me, it was superfluous. As was when I asked the question about the Rube Goldberg system, we had all these different things coming together. To me, that's interesting and it's fun, but if you spend 2 minutes during this presentation talking about that, it takes away from other things that even you wanted to discuss.
It's just similar to what Dr. Portero was saying. Yeah, you don't want to throw in all kinds of things that are not directly relevant.
And it was a hard thing to pick which one I wanted to discuss and which one I don't want to discuss. But I think the argument that we're having, or discussion that we're having, is about this. And considering this, we just put it into context. So, I mean, yes, we could have said we could have some scale, increasing scale perception, right. But we had it into context, okay, with this coming out of the valley. And yes, I think I spent the section 3 or 4 paragraphs talking about this, and what it is and how it's used and stuff. But I think it's a good way to understanding what we did. So.
Okay, so I have a specific question. Can you go to the slide where I was asking about the filter and the friction? I don't remember exactly what part that was. So other than the fact that it looks similar, what did you use to determine if your model was sufficient?
No, that's it. I mean, I just looked at the time and the amplitude and the trend. Most of all, the trend. You know, it is sufficient. Is it going to be perfect with? Is it going to be perfect with that? The setup? No, no way. Are you going to be predicted 100%? There's no way.
But was there any quantitative measure to say, all right, we're going to tune our model until we've reached this metric, or we're just going to tune it until it looks good?
No. See, that's one thing that I try to highlight while we're discussing this. If you take this friction model and you change the parameters of this friction model, you increase the static friction, the kinetic friction, all this stuff, you can mess with how this looks, obviously, right? You can change it. But I purposely wanted to measure the friction on this by applying this force onto it and by trying to pull this board out. Big approximation, but a very reasonable approximation. Okay, so pulling that board out, how much friction would it be of this being shut out there, right? And that's the friction model I use down there, and not just with this shape or with one additional shape. I use the same friction model, and it worked reasonably well. So as far as what, how I determined that it's good enough, is that what you mean?
Yeah, I mean, you're saying it worked reasonably well.
When I say reasonably well, I mean
it worked because it looked similar?
From displacement, velocity, and acceleration. So if I just pick displacement, that would be very biased. I think it would just be, well, it looks the same, right? But between those three, the way all three of them, the trends of all three, the amplitudes of all three, okay, the way it is with the with the friction model that I used and the setup that we used, I think it was a very good It was a very good model to use to predict that motion. So.
But to me, a qualitative description isn't sufficient to prove effectiveness.
Yeah.
It looks good, so it must be true, or it must be correct. Right?
So
if there was no quantitative goal,
yeah,
then how did you know when to stop? And stopping when it looks good probably needs a little more validation.
What do you mean stopping when it looks good?
Well, you're saying we tuned this friction model until...
No. That's the thing I'm not saying. I didn't tune it. I measured it with, by measuring this. That's the one thing I want to highlight, is that I measured the friction. If I were to pick a friction, tune a friction, then there would be a little tweaking. Right? So then you could say, well, big deal. You just change the friction to make it look nice. You know? But that's this. I remember the day that Dr. E came in, I showed you this. I said, I'm excited about this because it works. You know, because it was able to show similar trends, similar amplitudes, given that short of a time frame. It worked. I was really excited because I didn't use a tweaked friction. So I thought. So as far as, but let me ask you, is there something I can include in this rotation from today?
How you're defining it works. Right? So if you say the trend lines match, right, you can approximate the function of these lines and say, when my coefficients are within 10%, I know that it matches.
Oh, I see.
So
you want me to tell you some metric that I wanted to be within it.
Because if I had a plot that was a little different than this,
yeah,
and I said, oh, it also works, it looks good, and you would say, no, that doesn't look Mine looks better
Oh, I
than
see what you're
yours.
saying. I see
Right?
what you're saying.
Mine looks better than yours. That doesn't. Then you lose.
So,
I think you may find some kind of percentage-wise or kind of ratio
Right,
or
right.
in the literature or simulation studies,
I see what
how
you're saying.
they define it. Like, okay, this is relatively, sufficient enough to say. It's
very, very, very hard to find
Yeah,
that specific problem.
the term for it, structural error, that they use in mechanisms for when you want to, you have a desired function, you got to measure how close your design function is to it. So they talk about the structural error between here. So you might just see how that's measured.
I didn't even know about this.
Yeah.
See,
Yeah.
this is the thing about this dissertation. There's so many different concepts, and it's not one thing that I'm crazy special like I did not know about this. So I can look into this and try to quantify these results, but things like that. So as far as this, we ran the simulation, measured the thing, and this is what we got. Okay, so this was done. What is this? A month ago? This was pretty good for what it was. I mean, it's like qualitatively speaking.
Okay, I want to go quickly to the crutch here and talk about. You said it's more efficient. You said. I think someone asked a question and you said, well, the shape of the crutch makes it more efficient. That's why we want to do it. I'm wondering how you're measuring the efficiency. Is it just the efficiency of one step?
Here is, we are in the process, we actually did a study with the Cairn system that we have in IDR. And we changed the angles of the Cairn system, right? So we're in the process of doing another study and analyzing the data. So it's hard for me quantitatively to say it's more efficient. Did I take any oxygen measurements of somebody using it? I didn't do that. That would be a good thing to do.
But what did you, what simplified approach are you taking to measure efficiency?
What's simplified? So what we did was we used the Cairn system, we changed the angles. So something, simulating something like that. And what I want to do is look at the push-off forces, okay? So how you push off, at what angle you push off, the kinetics of a user using a crutch compared to a user not using a crutch. What differences can you see, if any? Now, for me to answer that question is definitely 100% more efficient. That would be a lie. I didn't know that, right? So that is what this upcoming research is going to show. And as far as, like I said before, I brought these crutches for discussions like this. If you feel like you want to be a judge of that, you can try to use them to see if it works. One thing that did not work, I have to say, so preliminary studies we did, was we ramped this angle up really high. And when you do that, it almost feels like it's countering what you're wanting to do. So that efficiency, I think, I'm predicting that it's a function of how much you're stepping up, how big this whole thing is, the change in radius. So there's a lot of these dependencies that go with that.
But you still haven't described how you want to measure efficiency. You say you're going to measure forces, you're going to measure push-off forces.
Kinematics and the way you push off at what angle and things like that. And that is, like
how does that get you to efficiency?
As I said, that is a simplified approach. Okay. Now here is a good indicator, okay, which I kind of mentions. So with that passive dynamic Walker model, this is the model, right? And we can use the model to make the shape that the crutch does, right? So for this particular simulation, I took the constant no curvature all the way to a lot of curvature. So going forward, like this way, the other way. Okay? So you're stepping here and the radius increases. So it's like the opposite that I explained with the crutch. Right? And the efficiency, the energy per step for the walker increased as you change the curvature. Which makes sense because this radius changes, and as it rolls on top of it, you're getting higher, right? Energy per step increases. So that is a good indicator that either you can take the crutch. So this particularly, you can take the crutch, turn it around, and go downhill, and you would have a more controlled descent. Right? Now, what I could not do with this model was turn it around and prove that it's more efficient. But I'm hypothesizing that this will mirror. So if you curve the other way, so if you go from big radius to small radius, okay, just this stem right here comes here, then this will mirror. It's more efficient. And that's what the theory of the crutch is. Like I said, that is just by increasing radius.
So you're measuring, so a system, you're saying a system is more efficient if it can go down less of a slope because that's less energy being input in the path dynamic walker per step.
So a path dynamic walker walks down a
right,
like you said, and so what I did was I took the distance walked divided by the energy off the walk. So it took, let's see how to explain this. When it steps, when it goes downhill, okay, and it goes up like that, it pushes itself up, raising the energy. Okay? That's probably the best way to describe it. That's the result of potential energy and also a combination of some kinetic energy.
Maybe I'll come back to that. I'm still missing a piece of it, but we can go from there.
I have no additional remarks. It did not damage already.
That when you test the clutches with the different information, let's say without any the shape, just a regular tip, okay. And then compare with attaching different shape of structure. Yeah. Then do you measure like from top, like the X-ray arm to the bottom? Is it equal
From the beginning to end?
No, I mean top to the bottom, the clutch size of clutches, length of clutches.
That is part of the measurement. Like I said, it's hard for me to state any data that we took or make any judgments off that. But as you say, you don't take any measurements from all the way top to the bottom.
No. My point is, your clutches, you hold them, right? Hold them. And hand this middle portion, your grab into, right?
Yeah.
And then also the upper portion, you're supposed to increase, right? Yeah. Then from top to the bottom, the length. What I'm saying is, the length of the clutches matters. Of course, that's why we are adjusting. So then, I'm wondering, you use the two different types of clutches, which is one is normal, the other one has a different shape underneath of the tip.
So what I did.
So the length is different or the same?
The length matters, of course. And if you have a short crutch, you want differently than a long crutch. What I try to do is from the total height of the crutch. So when you attach that shape to it, okay, you'll change something, right?
Mm-hmm.
So what I try to do is from the top to the bottom of the crutch, have it the same. Okay? But as you're rolling along, depending on the size of the kinetic shape, you're going from, if you wanted to push you, then you go from big radius to small radius. So you have this little drop of height, okay, depending on how big this is, right? So we wanted to make this much smaller than it is right now, keeping the radius change. But as far as your question, the height of the crutch, it was kept the same.
Kept the same.
Yeah.
You adjusted the.
Yeah, you can adjust these little things. So depending on the height of the person. So, but like I said, it's hard for me to give you any quantitative, firm judgments on how much energy it's taking. Is it particularly better in some forms of the motion and not in other? Hard for me to say that right now. But I can say this, with the kinetic shape, right now the way we have the clutches is a constant force. Okay, so it constantly goes this way. What if you change the force function to give you an initial force that starts you, okay? Then no force at all, right? Where it just lets you roll. Okay? To talking about the control problem, as in like it just goes. Well, maybe you can make the shape such that it helps you at the beginning of the rollover, and then towards the middle, it levels out or does something different depending on what it needs to do. That's where the argument of having a shape change with time at each step, depending on how you move.
If it's better for crutches, do you think it's going to be better for a shoe? You could make a very small shoe to do that shape change, and you think that's going to be the future?
They have the rollover. They have the SketchUp shoes, right?
Right.
The SketchUp shoes would arguably similar kind of thing where it changes in radius. You're stepping up. But for a shoe, it's a little more complicated, right? For a shoe, I highlighted the boots, the walking boots.
Well, 50 years from now, let's say the technology is there. Is that how our shoes are going to look? Are our shoes going to change the radius of the ground because it's somehow more energy efficient? Your perspective, your thoughts.
Yeah, I think that would be a good possibility. If you can, here's the problem with that. Ideally, you would have some shoe that can change in real time the shoe sole, right? Depending on if you're walking on grass or something, maybe the stiffness of it, one, and two, the shape of it, okay? And you could change it, but the problem with something like that, you need something that changes length and is really stiff. Stiff enough to roll over, but loose enough to change shapes all the time. That's what we want to do with the crutch. We want to put little spokes in there to change the shapes. But you can also do this in rehabilitation, which I did not mention. It's a really cool thing. If you take the 3D concept, the 3D shape concept, you might be able to apply a force going this way, like normal, but also a force that twists around. So if somebody has maybe joint problems in the hip or the knee, you could repeatedly, every step, force the knee to go one way or the other way, to prevent it from buckling or some ligament damage or something like that. So maybe you can use the 3D shape on the shoe sole that guides the user's motion of the foot, of rolling over, depending on the force of it specified. So you may be able to do that. So yeah, I mean, could be a possibility. They told us we would have hoverboards now.
Just a question on this. If you, when you do this in the Karen system,
yeah,
you can measure the ground reactions, right? So you know how much, that's where the work is going into the system, or the forces are going into the system.
Yeah. As far as like the walk, just walking in general?
Yeah, or can you do that with the crutches?
Yes, that's what we did with the crutches.
Okay. Can you also measure whether the velocity, the center of gravity?
Center of pressure?
No, the body's actual center of gravity, where it's moving, how it's moving.
If you approximate the anthropomorphic model, as far as there's many of these models out there that approximate the body as lump masses, right?
Right.
You know where your markers are and how they move. Now you can approximate the motions of it as far as, and you can calculate the center of pressure. So if you say this thigh is one lump mass right here with the center of pressure, center of gravity here.
Right.
Looking at the motion tracker, you can approximate what the center of gravity is. So yes, you can do that pretty easy.
Yeah, so what I'm saying is if you know your forces and you know your velocities, do you know what your power is instantaneously?
Yes, you could figure that out indirectly. Yes.
And could that tell you whether you're using more or less power when you're using your crutches?
Yes, indirectly. And that is a possibility of using kinematics and kinetics to approximate the efficiency. So you could do that, yes, and like I said, the data analysis is still yet to come.
That is essentially my question. What if we had a whiteboard here? I would ask you, you're going to measure energy by saying E equals what, and what would you put there? How would you, what would be your equation for?
You would look at the work done. So you would look at the change in energy, change in potential, and the center of gravity. You look at how it moves and where it's at, and you would look at for each step what it does. So I think that would be generally what I would try first.
One other specific one. If you go back one slide. The Handzic paper. They have a metric they use. I don't know what it is off the top of my head.
But I know what it is. So what they do is
it's one potential one.
They look at the redirection of the velocity of the hip. So when you step this way, your hip movement is this way. But when you come down here, your hip movement, your velocity is down. So this change in angle, it's a really rough approximation that they use. It's a good paper, but they have this indirect approximation that they take the change in velocity and approximate how much work is used to walk. And they show like the actual energy and their approximation, which works pretty well. I think I cut something off here. It was a label. It labeled this. This might have been their approximation. But this is forces. My bad. There's a different one for that.
And you're going to use that same metric, you think?
It's a possibility.
Okay. So that was kind of working toward what metric you're using to.
Yeah, it's a possibility. So that could be. So they're using forces and this change of velocity to approximate how much energy somebody takes to walk. And there's literally a lot of models that can approximate how much energy you can use. You can use that with oxygen consumption to mean some kind of apparatus. You can use this with kinematics, all kinds of these approximations. So I mean, so yeah, I think that would be a good starting.
So while you're using clutches and which part of your body, your extremity, you would think using more upper extremity or lower extremity while you're walking with the
I think it's more upper extremity, much upper, because the way you use a crutch, you don't lean on here. You have to support yourself.
That's
right?
correct.
And the way you hold a crutch, a lot of the energy comes from up here. But if you're just, I'm not saying that it's going to alleviate all the energy needed, but it's going to alleviate some.
But I'm wondering if you, hypothetically, you're measuring some kind of muscle torque, the shoulder joint or the elbow joint or even wrist, any kind of gripping force or something, you can measure it, and then they can be maybe repeaters, or something like you can compare to using just a regular process. I mean, that can be utilized.
No, definitely.
Put into your equation.
You can, with that logic, which I haven't thought of yet, but with that logic, you can take a quantitative scale that you can measure, like you said, the gripping force. That's a good indicator. The tightness of muscle and how much energy you're using, or how much, like you said, torque you're applying to push yourself over. That's a good metric. Okay. Now, depending on what you want to look at, if you want to reduce that, great. That's a problem. There's a lot of designs. This is a basic crutch. There's literally hundreds of designs and patents that I've looked up. They have all kinds of stuff up here. People holding themselves up somehow just to alleviate that stress that you were talking about.
Sure, and by changing the bottom, the tip, the shape of the tip, and then you can, reduce some of the force torque you apply to your upper extremity. That tells them a lot. That's a lot of things, especially when you deal with the patient with the upper extremity weakness. Like, for example, let's say we apply some different types of clutches, but I'm talking generally. Let's say, kind of SCCI patient. Okay, people with spinal cord injury. They have limited, very big. It's not. I'm not talking complete, like incomplete. They're somewhat strengths to that low extremity. They cannot do much a lot with the low extremity, so they have to rely on their upper extremity mostly. Then, I mean, energy efficiency is very important for them. So by changing the bottom there, it's going to help them a lot. When you mentioned about speed, how fast they can move, walk forward. How they have.
Yes, I mean, people with exoskeletons use crutches and things like that. And all that, like you said, is upper extremity. And you're right. I mean, if it can alleviate 5–10% of whatever energy they're using, that's a success.
Exactly.
So, and like I said, for the 5th time, I think I said, it seems to be the prime subject, but it's hard for me to make any judgments without looking at some data. Hopefully, which will come within the next month or so.
All right. Any other questions from the
Maybe just one last question. You have one of these slides that refers to figure 4.1. I don't know if you know this one. I think you showed this also.
Oh, okay.
Where you will come up with
the main genetic shape thing.
Yeah.
This is the motion one, or
yeah, this is the
motion.
Yeah, I don't know.
The one that's
I guess the
moving,
one
or
before that. Yeah. It's the same kind of diagram. Yeah. So this angle psi. I mean, it's two difference in the two. You have reference. The right one is reference number 207 or something. I mean, if I look at this equation, you're relating dr d theta, which is, I'm assuming that's the slope, right, at the contact.
right? Slope at the contact.
So you're saying that the slope at the contact is equal to r divided by tangent of psi. I think one of the equations. Yeah, the equation at the bottom right. Yeah. So I'm a little confused about the two sides that you're using on the right side and the left side. The one on the left, I guess, it doesn't really, does it? Can you explain why it depends on the slope, dr d theta? I mean, from the diagram, it looks like it only depends on the offset and r.
So, just from the beginning, these two drawings, I know. These two drawings are basically saying a little different. Here, the slope is taken at this point.
Mm-hmm.
Here, the slope is taken at this point, right? But if you take this slope and put it exactly at that point, it's the same angle. But as far as like the relation between those two forces, so if this offset here is that angle, so that's the way the geometry is. If you take the applied force down to be perfectly perpendicular to the ground. So that would.
So this, I guess, the bottom right equation tells me that the slope is dr d theta is tangent of psi divided by capital R, or I guess, tangent of psi is.
Yeah. To rearrange it.
Tangent of psi, which really depends on the offset.
It depends, on the curve and how it's.
Does it depend on the curve, or does
it depends on the change of the curve and the curve. I mean, if there was no curve, if this was a perfect circle, then psi would be 90 degrees and there is no offset. Or I'm thinking that's what you mean by offset.
Well, I mean, you can have a circular wheel and then offset at that point. It doesn't have to be on the top. You can have the force acting. I mean, a circular wheel, but an offset, not at the force not acting on the center of the circle, but from the.
You mean if you have a wheel with an axle in the middle, in perfect middle?
Not in the middle, but
on the side.
On the side.
Yeah, of course. That would also define this equation. However, if you do that, then what's the point of having the axle in the middle? Then you know the axle is where the instantaneously it would move the same as this if you have some kind of change there. If you have a perfectly forward circular wheel,
circle but an offset.
Right, an offset, and you put a force down. Instantaneously, it would move the same. Yes. But continuously around, you have to change that force application every time you come around. You have to know where to apply that force, which is similar to what I'm doing there by having the axle there.
Anyway, I don't want to extend it too much. So thank
No,
you.
it's fine. I explain.
All right. Any other questions? Dr. Reed, do you have a question?
Yeah, I have one last one. Anyone else have a question? So, I hate to belabor it more. The crutch.
Yeah.
Would you mind actually getting that? I think it might help to have people understand. If you have someone demo it,
yeah.
If you want to go get a volunteer to grab some crutches and.
Is there an IRP for that?
Somebody healed that. Actually, someone with an awkward foot shape would actually emphasize my point further.
Oh my god. Okay, so what do you want?
All right, get the crutch.
I'm so sorry.
You can.
No.
Maybe you get one crutch because that's how you use it.
Yeah, you want two, but you might actually want to adjust it to her height.
So.
I've never used crutch before.
So while I was doing this rotation, I think I was a complete year. I was just completely immersed. I was just sleeping at the lab. Just trying to develop these things, right? And I was dating her for the last 2 years, and it was she always brings me food and stuff, and all this good stuff. And took care of me, I'm like a cave animal in the lab, right? Just trying to get some sunshine. And she would come and make me forget stuff. But so I have to say thank you, Bob. Okay. And I'm telling you, one day I'll ask her to be my wife. One day this will happen.
What are you waiting for?
I don't know. I think today might be the day. So I think what's this? So I think this might be the day. And so while this God set on some stuff with me, he watched something result. So yes, I didn't
It's okay, you can be
I use a crutch. Boy. Good Keep the box. Thank you for all
She's living a lot of the crutch.
She's a great cook.
All right.
So that's it. So that's the presentation. Thank you. I thank the committee for taking it up.
All right. So let's excuse everyone, and the committee going to discuss and deliver.
I got it. Oh my god.
Well, never more than.
I think you put out your, I'll get it.
Oh,
Yeah, keep talking.
What are we doing?
So,